Yeah. All right, so I apologize. You guys might not be able to see me. Yeah, you can kind of see me. I can see over the screen. All right, if you're ready, let's get the party started, shall we? So our unit 5 is going to be ignition systems, but this is part 1. Part 1 is going to be all about the system, the components, how the system works. There's a lot of different systems, so ignition's a really tough thing to cover because it's like we could teach you all about coil on plug ignition systems and you'd be like, oh, that was easy, but then you pop the hood on something else and it'll be like a waste spark or a distributor style or an older HEI style. There's like 1,000 types of ignition systems. So we got to go over quite a few of them. And then part 2, which will be much more simple, not simple, but much more brief and condensed, is just going to be diagnosing it, right? So why would we want to know about this? Well, let's say the car comes in and it has a misfire. A misfire could be loss of compression. We covered that extensively, right? Now you guys know how to check compression, check cylinder leakage. You could do the vacuum test. You could do the power balance test. You could do some stuff with the scan tool now. But another possibility is it's a no spark condition. So if that cylinder is not sparking, that would cause a misfire. And your common DIY approach is like, put spark plugs in it. And you put the spark plugs in it, and it might fix it actually, but it might not fix it. And then if the spark plugs don't fix it, then you go ahead and you put coils in it. And then that might fix it. But if it doesn't fix it, you get to call the customer and say, hey, I guessed once and it was wrong. And then I guessed twice and it was wrong. And if you sue me and bring me to court, I'm probably going to lose because I'm not going to have a good reason for replacing those parts, right? So we got to get away from the guesswork and get more into the diagnosis. So that's really what this and the part 2 is going to be about. You need to know part 1 to know part 2. So let's jump in and just do an overall. So this is like a more modern, typical engine right here. You can see we've got this coil going right into that cylinder. That's what we'll call coil unplug. The coil is on the plug. Cool. So you'd have 3 coils here, and then you have 3 back here. So this is a V6. These coils work in conjunction with a camshaft position sensor and a crankshaft position sensor. And there's, of course, a little bit more that's going on. So one of the things that we're going to cover is what controls the coils. And generally, that's going to be the ECU. But how does the ECU know, exactly what the position the crankshaft's in? That's going to be the crankshaft position sensor down here, right? So there's a lot of little pieces that go into the ignition system on a fairly modern engine like this. And then let me give you a cool story that I think will help you continue to understand why we're talking about this. I don't remember if I told you. Think I think I did. I had a girl call me. She feeds horses for one of my neighbors on the ranch, and she's got a check engine light, and she had a misfire. And so she called up a mobile mechanic, and she's telling me this story, right? So this is her story. I didn't verify a lot of these things, but she called up a mobile mechanic and said, hey, I've got this, my truck's running bad. The check engine light's flashing. It's pretty typical misfire. Mobile mechanic comes over and he's like, hey, you need a coil, and she also requests he does an oil change, right? So from her words, she said he ran a diagnostic, which is always, I'm kind of like, what do you mean he ran a diagnostic? Like, what did he do to diagnose? And he's like, yeah, well, he came over with this machine and ran the diagnostic. And I'm like, all right, it sounds like code check. Sounds like just retrieve DTCs, something you've all done now. And then I said, and yep, and it needed a coil. So he went and got the coil, put the coil in. And I was kind of like, did you see any other tools besides the scan tool? And she's like, well, he had the diagnostic machine. And I was like, yeah, I think I'm going to take that as a no, right? So it sounds to me that the mobile mechanic showed up, checked codes, saw that it had a misfire on a certain cylinder, replaced that coil, and she requested he did an oil change. Anybody want to take a guess at that bill? Now I'll know if I told you the story. You did hear the story. $1,200. You nailed it. Apparently you and this mobile mechanic are in the same wavelength. $1,200 and left. And then, well, it didn't fix it. Shockingly, yeah, it's true. So it didn't fix it. And $1,200 and it wasn't fixed. And then I kind of probed around a little bit more like, well, did you even like drive it or start it? Like you should have known that it wasn't fixed. And then this is where it got a little more weird. It was like, well, it fixed it for a little bit, but now it's a new cylinder. And so the facts got really muddy right there. So I'm not exactly sure of what really happened, but I said, okay, so now what's your plan? I said, well, it's got it's got a code set, and my other friend checked it, and we've got this DTC. I have the code in my phone, but it was basically ignition coil 3 primary circuit. And I'm like, oh, all right, that makes a lot of sense. And you said that that coil's new? And she said, yeah. And we also changed the coil from 3 to 5, and the code stayed on 3. So think of what I just said. If you move the coil from 3 to 5 and the coil was bad, wouldn't the code follow to cylinder 5, but it's staying on 3? Something with that cylinder. Exactly, right? So like this is just basic, diagnosis without a ton of knowledge. And so I said, well, what are you really trying to do now? Because I'm trying to feel out like is this a situation where she's looking to hire me to come do to come do the diagnosis, or is this more like a give me some advice? Because if somebody calls, and I'm not really that busy, I'm happy to provide some sort of like advice, right? But if the person's talking about come over and spend time actually diagnosing, that's like a whole different thing. So I was running around trying to help a lot of people, and I found out everybody and their brother wants a diagnosis, and they kind of think the diagnosis is free. Remember we talked about AutoZone and O'Reilly's, they'd run a free diagnosis. So they think I'm like going to go over there and just check a code, but I'm sort of like, for $24, you guys all saw it, you could buy a code reader on Amazon, it'll ship tomorrow. And then you don't even need me at all, except it's still not really diagnosed. So I kind of told her some of that. And then I said, well, look, to really do the diagnosis, you got to know a lot about the system. And for me to get involved, I'd have to come over and spend a minimum of an hour to really determine like what the cause of this DTC is. And my minimum to even roll out's $100, which I more recently put into place because too many people were calling for diagnosis, and I'd go over and be like that head gasket problem where there was no rhythm to the crank, right? It was, and I look and I do a couple quick checks, and I'm like, we didn't talk about my minimum charge. So like, yeah, this engine's cooked in your terms. Like, just don't fix it, but I'm out of here. Bye. No charge, no nothing. I really can't justify doing a whole lot of that. So I give her that, and she says, no, I really just want to fix it myself. I want to save the money. And I said, all right, cool. But that's why I found out how much she paid. And I was like, yeah, that makes sense. But sometimes hiring a person, you're going to spend less to hire them to diagnose it than you are to go down and buy your own parts and put it on if it fixed nothing, right? So you're already into it for a coil. And she said, well, I can't afford it. He charged me $1,200 for that. And then I was like, oh, okay. Yeah, now I understand why you're trying not to spend any more money, because you emptied the clip on this, totally missed the shot, misdiagnosis. Like she's wiped out. I totally get that. So just talking with her a little, I said, well, I'll tell you what, give me the exact code you have. And when I saw that it was that primary ignition circuit, I knew the primary ignition circuit is partially in the coil, but all this down here is going to be secondary. And we're going to get into why you have to know the difference. And she was like, it's got to be the spark plug, right? Because I moved the coil from 3 to 5 and it didn't follow. The only thing left in that cylinder is the spark plug. And I was kind of like, cool idea, but what's the holdup? I can't get the spark plug loose. I need a longer ratchet. And I'm sort of like, all right, let me be a little more harsh, but also helpful. If your struggle is to get the spark plug out, and that's what you've been struggling with for a couple of days while you've been waiting for me to return your call, like you don't have the skills to diagnose this problem. Anybody, like a literal monkey, like an animal, like a some sort of a primate, could get the spark plug loose and put a new spark plug in. But if the struggle is getting the spark plug out and putting a new spark plug in, and we're not even remotely starting to enter the discussion of what the primary circuit entails, like this is just out of your skill level. And, that wasn't very well received. I just said, it's up to you. I mean, I could give you the advice, but it's up to you to take it or not. You could call the mobile mechanic back, and, he'll come back out and replace some stuff. And then she's kind of like, no, no, I don't want to do that. Why don't you tell me what you think? And I just said, the primary circuit is the small wires going to the coil. You need to find out if there's an open between your ECM and the coil. And where we live, mice probably chewed that. Right off the hip, I'm going to bet you, mouse chewed the primary side of the circuit. And she's kind of like, the smaller wires? And I said, yeah. So she sends a picture of the small wires going to the coil, all sorts of jacked up. And I'm sort of like, stop right there. You need to fix that. Forget about the spark plug. Forget about all that type of stuff. You need to fix those small primary wires going to the coil. And then probably that's going to fix the whole thing. But if it doesn't, I'll give you your next steps, right? Don't call anybody else. Don't go to the parts place. Don't try to get another coil. None of that. Just fix those wires, cool? Because the code was for the primary circuit. Okay, so just keep this in mind. How could I give her so much advice over the phone? Well, as we get into this, you'll start to understand the system. And if you understand the system, then you can kind of know which way to go. But apparently, I don't know if it was the mobile mechanic or her friend who had the scan tool, but somebody was convinced that it was the spark plug setting a primary circuit code. No, it doesn't work that way. All right, so let's jump right into there. Here's what's happening with your ignition system. We've got this part right here is the coil. So it uses quite a few different little scientific theories and rules and laws, such as electricity, voltage, current, resistance, and magnetism. So kind of the summary would be, we're going to use one side of this coil with low voltage. So you guys know what your battery voltage is? 12-ish, yeah, 12 if it's running, 13, maybe 14, right? So we're going to use that relatively low voltage to create a very high voltage, because ultimately, as you'll see a little later, we need high voltage that's going to actually jump the gap in the spark plug. Your battery can't jump a spark plug gap. You know, that gap could be like 1/8 of an inch, maybe even bigger. So no. So when we get into this coil, I'll show you exactly what we got. But for right now, just know we're going to use all these scientific principles to achieve our goal, which is taking our 12 volt or so primary ignition and make it into 40,000 or so secondary ignition voltage, which is what we need to jump the gap. So how do you turn 12 volts into 40,000 volts? Well, it's kind of like, you know, everything comes with a cost. I wish it was kind of like money, but like you could take $12 and run it into this machine and it'll spit out 40,000. That'd be nice. That'd be nice. But like anything, there's a cost, right? So if you want a major increase in voltage, you're going to see, I'll prove it to you mathematically. You can have that, but you're going to have a major reduction in amperage, which is actually fine because we don't need a lot of amps to fire the spark plug. We need a lot of volts. Okay, so when we get into that, I'll show you. This coil operates on all these principles, electromagnetic induction being one of them, right? And then in a coil, also, you should know the conductors are stationary. So when we're looking at these coils of wire right here, those don't move. The magnetic field does move, though. The field will fluctuate. So we're going to make a magnetic field, and the magnetic field can move, but these don't move. Okay, so when we start talking about the coil, the primary coil and the secondary coil, those are fixed. They're not moving around. Okay. And then there's a couple different forms of limitations, so we do need to limit the current on this. But as we jump in, let's define some terms. Do you guys know what a conductor is from electrical? Something that exactly, yeah. It's got, look here, it's got a low resistance for electron movement, right? So that means it's a good conductor, means electricity will flow through it. If it's got low resistance, that means the electrons will flow easily. The more resistance it has, the harder it is for the electrons to flow. Don't you make me pull up a picture of the tattoo thing with the thing. You know what I'm talking about. All right. And then let's define resistance. Resistance is just the opposition to current flow, which we'd measure in ohms, right? So when we start talking about the conductors, just know that's like, you know, iron, silver, copper, something like that. Resistance is the same as resistance has always been. It's opposition to current flow. Cool. And then electromagnetism is going to come in. When current flows through a conductor, it produces a magnetic field around the conductor. And that's kind of weird, but that's just the way it is. So anytime that, even with a wire, if you have current flowing through a wire, it will produce a magnetic field. Like they have these short finders, and the short finders measure a magnetic field. I've even heard of old-timey people using a compass and running the compass along the wire. And when the compass flips direction, you know that that's where the open in the wire is. It's kind of like cool sciencey theory stuff. So just in general, no, when we flow current through, let's say, that primary conductor, it's going to create a magnetic field, okay? And then there's ionization. That's when the coil's high voltage discharge across the spark gap causes the electrons in the air-fuel mixture to split and form a conductive path for current. What? So literally when the spark occurs, it's going to take those electrons, because there are electrons in the air-fuel mixture, right? We're generating electrons and firing it across the spark plug gap, but in the air-fuel ratio, there's electrons, right? Like if you look at oxygen, there's electrons in that atom. So we're going to basically take those electrons, and they're going to split and form a conductive path. So there's basically an alignment of the electrons within the cylinder, only where the spark is going to conduct. That's like kind of what happens with lightning too. You can actually measure that, which sounds kind of weird, but that's one of the ways we can run diagnosis on the ignition system. So as we get into this, you'll see the ECM or the PCM or whatever the control module is can monitor the ionization to determine, like, did the spark occur? So if the spark does occur, it'll align those electrons in the air fuel mixture, and the ECM can detect that that occurred. If there is no spark, you know what won't happen? This. So if the spark doesn't go through it because of, the spark plug is no good or the coil's no good, we won't get the ion activity, and the ECM can determine that there was no spark. Okay, we'll come back to that. Then a magnetic field. So what we're starting to ramp up into the magnetic field is, like, if we run that current through the primary, it creates a magnetic field because magnetism is generated with the current flow, right? Well, we want to make a magnetic field. This is kind of like building up. This is a ramp right here. We'll come back to this ramp mostly next time, but this is building up that coil, and it's going to create a strong magnetic field. But then what's going to happen is, when we go ahead and we turn off the coil, it's going to create a voltage spike, which we may call a kickback voltage. Sometimes we'll call it CEMF, counter electromotive force, is generated in the primary winding. All right, so wait a minute. What just happened? We ramped it up like this. We ramped that up by giving that coil 12 volts in ground. Then all of a sudden, we take away the ground. Technically, you could take away the 12 volts, but typically we take away the ground. When you take away the ground, this magnetic field collapses, and it's going to actually make a kickback voltage. And then sometimes we'll even call it a flyback voltage, right? But that's going to be very critical, and I'll explain to you why. And the clue is back here, we were talking about the primary and the secondary. You notice that these don't touch, right? So we want to start on the primary and then have the electricity be transferred into the secondary. But I already explained these don't move and these don't touch. That's all got to do with this. So the way that it was explained to me, which makes a lot of sense, is if you create a magnetic field in the primary, it's going to build a big magnetic field, and then you immediately turn off the ground, that magnetic field is going to collapse. And as you can see, we'll talk about the kickback voltage. That's going to induce it over into the secondary. And so that's how we're transferring the energy. It's going from the primary to the secondary, mainly due to this. So this is more saying, like, this is how a magnetic field works. Cool. And then just as a note, depending on the manufacturer, some of them monitor the flyback voltage to verify the coil operation. Other ones verify the current buildup. Some of them even check the ionization in the combustion chamber, right? So there's different ways to monitor this. Cool. All right, so if you look at this, during the diagnosis, the PCM, so the computer, compares the current measured to the present high and low values to determine integrity. All right, it's kind of interesting. It's interesting how the ECM is able to monitor this, okay? And if the value is above or below, the PCM knows that the proper ignition cannot take place and stores a primary circuit diagnostic trouble code. Okay, we're going to come back to that a little bit. So basically what we're saying is it's going to watch the current, like back here. Remember we had this right here. Remember how this current built up? That's like a really clean, good ramp up. If this ramp is abnormal, it knows that the primary side of the coil is not doing what it's supposed to do. Okay, so that's what we're getting into. Okay, and then as we get into the secondary circuit, let's take a look right here. Here is your secondary, here's your primary. You notice the primary doesn't touch the secondary, right? But we were talking about that magnetic field. If we create a magnetic field in the primary, and then we collapse it by turning off the ground, all the energy in these coils, and more actually, will jump into these coils. Okay, so that's kind of the direction that we're going here. Right, so what that means is the high voltage induced into the secondary windings from the collapse of the magnetic field is increased by the number of turns in the secondary compared to the primary. So look at this, it's a little hard to see, but the primary has a relatively small number of turns in the coil. You know what the secondary has? A lot, much more. So remember how we were saying we wanted something that would take us from 12 volts to 40,000? Well, that's a big part of what we do. We only have a few turns right here. And then right here, we have a lot of turns. So that lot of turns is going to react with the magnetic field a little bit different. Like the magnetic field induces current, but it depends on how many coils of wire. So if you wanted higher voltage, how do you think you'd make a higher voltage on this coil? More. The more windings, more circles. It's going to do more circles on the secondary ignition coil.
What
So
those circles are like a little battery, and then like you're connecting those batteries in series.
I don't understand your question.
Like is that how it works though?
Well, if you look at this right here, the secondary coil winding really goes to the spark plug. But the primary coil does kind of go to the battery, but it goes like to the 12-volt battery, but it goes through the ECM. So some of those experiments you did in electrical would be like you do some windings and you connect it to a battery and you can make a magnetic field. I agree with that. If you were to take these windings and put 12 volts here and ground here, you'd actually generate a magnetic field. That's accurate. That's what we do. But then you know what we do? We break the connection. When we break the connection, that magnetic field collapses and it induces that energy and more into the secondary. And the secondary is at a much higher voltage. And so you'll see in a couple slides, we talk about, well, how did we just increase the high voltage? It's not magic. Well, there's a cost to that. And there's a couple other interesting things that happen, right? So if you look, this is your primary. That's going to be the side that gets your small wires. And this is your secondary. That's going to be the side that gets the spark plug. Okay, that's the first little lesson. So a lot of times people will get a little stuck on like, how does that coil make the spark? Well, through this, the primary winding inducing into the secondary winding. But for the primary winding to work, as you'll see, we need a good 12 volts. We need a ground, and then we need to take the ground away, and that's going to start the spark process.
So the primary is just
in a way, you could call it that. Yeah, the primary makes the secondary, but we can easily control the primary with a computer because Computers like 12 volts. Computers don't like 40,000 volts. 40,000 volts lets the magic smoke out of the computer, right? So that's kind of a breakdown. And don't worry, we'll get a little more into it. But if you notice, we've got this secondary shown. We'll come back to that too. And there's, depending on the ratio of turns between the primary and secondary, that's going to determine the voltage increase and the amperage decrease in that system, right? And so, you know, if you look at like basically all a coil is a step-up transformer. So what I mean by that is you put 12 in and it steps it up to 40,000. Some coils could be less, some could be more. Some on some really like racy stuff could be 100,000. So you guys have seen the MSD, you know, super high power coils. Sometimes they want to run those at like 100,000. So if you want to run at 100,000, that means you're going to end up having to have a different ratio of primary into secondary. So that big high powered MSD coil is going to have less primary windings and more secondary loops around the winding to make the higher voltage, which has an application. But let me just say, having a higher voltage on your stock original OEM daily driver car, there's no benefit there. But as we get in a little bit further, when we start trying to run boost and we start trying to run higher compression, we start trying to do, you know, some high performance applications, it actually it makes it harder for the spark to jump the gap. So to make the spark jump the gap, we actually may need higher voltage. That would be good application for that MSD super duper duper high powered ignition. But if it's stock, no. Okay, makes sense? So that's really all it is, a step-up transformer. And the ratios, if you read the book gets really into the ratios and how and why and more the engineering aspect. I usually stay pretty light on that because, you know, if you overall understand this concept, you don't need to know all about the ratios. Like when you go to the parts store and you're like, hey, I need an ignition coil for my 2008 Honda Civic SI, they're not gonna be like, well, how many what do you want the coil ratio to be between your primary and secondary ignition? You're gonna be like, what? Like, I don't know. They don't know. You don't know. We don't know. The engineers know because that's what they do. Makes sense. So I stay a little bit light on some of these ratios, maybe 1:8 or 2:1 or whatever. And then a few more terms. So electromotive force is the pressure or push generated by any source of energy that causes electrons to flow in a conductor. You know what that means? That's just voltage. That's just voltage. Voltage is electrical pressure. So when we talk about voltage, it was 12 volts. Now it's 40,000. That doesn't mean it has more power. That means it has more pressure. Make sense? So if you were to take, let's say, like a big old fire hose, like this big, and you were to hook that up to your little hose spigot, do you think it's going to have more pressure, less pressure, the same? It's probably going to have less pressure, but it might have more flow because it's a bigger passage, right? But that doesn't mean overall that it's any more powerful. Like, let's think of a pressure washer. You ever notice a pressure washer sprays at really high pressure, but it's still got your same garden hose going into it. So the pressure washer increases the pressure. It's smaller. Yeah, it's smaller, higher pressure, but it's not going to necessarily be more volume, right? So, oh, a water jet. Yeah. So you could run very, very high pressure water and actually cut through metal. That's true. It's not, but you see, it's kind of like a pressure versus volume are different. And that's the thing I want to make sure you understand. When we're talking about voltage, that's just the amount of electrical pressure. So when we went from 12 volts to 40,000, we increased the pressure on those electrons massively. So now they can jump a gap, right? If we were running a 40,000 volt battery in your car, you wouldn't even need to hook up the battery terminals. You just need to get them within about that far, and the electrons would jump out of the battery and go right into your battery terminal. It'd be pretty gnarly. You'd also get the crap shocked out of you when you went to touch that battery. Make sense? So did you guys know the ignition system can shock you? Do you find that shocking? It can shock you, but do you know why? It's higher voltage. Higher voltage has enough pressure to push through the air and push through your body, and you'll feel it, and you will be awake and you will be alive. But you know why it's extremely almost impossible to kill you? It's higher voltage, but it's lower amperage. So high voltage can push through your body, but it's not such high amperage to where it's going to throw your heart out of rhythm and start shutting your, system down. Makes sense. So that's kind of the direction that we're going when we talk about this. Electromotive force, boom, higher voltage. And then when we start talking about inductive reluctance, that's reluctance opposes the expansion of magnetic lines of force called flux. So these coils do have some inductive reluctance. And additionally, inductive reactance is opposes a change in the current flow through a coil. Every time the coil is switched on, the current flow is going to increase. Every time it's switched off, the current flow is going to decrease. That's kind of like electrical works that way. So if you turn the switch on, increase in current, right? What happens if you turn the switch off? Decrease or no more flow. Yeah, exactly. Right. So it's just we're using these scientific terms. And inductance is the transfer of energy from the primary coil windings to the secondary. All right. So what? Hang on. Look at that. Remember, we had the primary and the secondary. The inductance means this energy is going to jump into this energy. All right. Who's got a phone that does wireless charging? Boom. Inductance. It induces energy into your battery without physically making an electrical conduction. See what I'm saying? So you got old school, like this one, I think does wireless charging. I just don't have a wireless charger. I plug in like this. We're literally doing direct contact electrical flow. But if I put it on the wireless charging pad, we're going to induce it. Okay, makes sense? That's kind of what it's saying. Inductance is where it transfers. It transfers from your charging pad into your battery. It transfers from your primary coil into your secondary coil. Cool? Kind of get me so far? It transfers 12 volts into this very, very highly wound, lots and lots of loop secondary, which makes 40,000. All right? Not really magic. But like anything, there's a cost. So here's Watt's law. You guys, power. So, in Watt's law is V times I. Can you see what that means here? V times I. So what's that? Volts times amps. Cool. Let's do a little measurement, or let's do a little example. Let me bust out my pen here. I think this should work. I might pull it over here just so I can see better. Let's do a voltage of 12, shall we? 12. Nah, orange is going to be a bad color. How about blue? 12 volts, cool. Times how many amps do you want to do? I don't know. Let's say 5 amps. It might be less, but let's go with 5. 12 times 5. Can anybody do that? You guys know how to do it? All right, 60. The next one might be a little tougher. So 60. So that means P equals 60. So see, the way you do it, if you want to calculate P, you'll block P off and you're left with V next to I. It's V times I. If you had P of 60 and you had V of 12, you could block off I and you do P divided by V. Okay, makes sense? So Ohm's law, this is very similar to Ohm's law. It's just Watt's law, right? Same type of concept. So we have a 60 watt coil, let's say in this case. All right. What about this? If we were to, right, the coil makes, for simplicity's sake, let's say the coil makes the same amount of power on each side. If we have a coil that's 60 watts, let's just think about how we could get 40,000. See, the V is going to become 40,000. Or you know what? Just for simple math, let's make it 12,000. If our V is 12,000, what would our formula be? It'd be P divided by V. Okay, it'd be P divided by V. So 60 divided by 12,000. Actually, that math isn't really that simple.
0.005.
All right, let's do it together. 60 divided by 12,000. Do you guys understand how I went from 12 to 12,000? I'm just saying if we want a coil that's going to fire at 12,000 volts, I'm going to say it's a 60-watt coil because we already calculated that. And then I'm going to say 12,000 will be like this. I need to set this down and use the regular marker or the regular thing. It's going to be 60 divided by 12,000. So that means we have 0.005 amps. As a matter of fact, through scientific law, that would work. So the amps is no longer 5 amps, it's 0.005. It's not even close to 1 amp. It's very low. But that's what I'm saying. If you want 12 volts to become 12,000, no problem. You can have that. But it doesn't increase the power. You get me? It's only a 60-watt coil. So if you wanted 12,000 volts, you can have 12,000 volts, but you can only have it at 0.005 amps. It's very low amps. So remember, like kind of what I was saying is the high voltage ignition system, secondary, will shock you, but it won't kill you, right? It's going to be high voltage at low amps. So you're going to be like, yeah, oh, that was like, I don't like that. But it's different than being electrocuted. You know, so if you were to go into like your breaker panel at home and you were to touch the wrong things, that could kill you. Exactly. It might only have 240 volts, but it has high amps, right? That's like a 200 amp service. That's you're cooked. I mean, quite literally, some of the people who've been trying to steal copper wire, they don't, you know, they're tweaking and everything, and they try to steal copper wire, and they end up getting stuck on there. I'm dead serious. I've talked to some electricians I used to work with. They'd go and they'd find, like, they found one. This is kind of gross, so just either plug your ears or don't. But they found a guy trying to steal the copper wire, and he looked like he was a hot dog that got left in the microwave. He was just literally like cooked, about to pop, and his buddy tried to grab him, cooked him too. So like when it's high voltage and high amperage, you're done. When it's high amps, like the battery could have potentially hundreds of amps, but it's 12 volts, it won't push through your body. So if you wanted 12 volts to become 12,000, no problem. But it's going to be at a massive expensive amps. That there's just the universe is like so precise. You know, you can have 12,000 volts, but if you want 100 times the voltage, you're going to get 1/100th of the amperage. It's a mathematical proportional calculation every time. It's not just kind of like random. You make sense? All right, so overall, I think that should kind of just help you understand why the coil works the way it works. And I don't ever plan to do any math on that again. It's not really like what I like to do. If I want to be an electrical engineer, maybe you want to be an electrical engineer, you might be an electrical engineer that designs ignition coils, and you will know every intimate detail of the secondary ignition system and the calculation and the number of windings and all this type of stuff. But as technicians, you just need to be able to look at that and be like, that's going to take 12 volts and turn into something more. Depending on the car, it may be 40,000, 60,000, I don't know, some number. Relatively low voltage with relatively high amps will become very high voltage with very low amps every time through that calculator. Cool. All right, now here's some other interesting issues. When we start looking at waveforms, especially in the part 2, we need to diagnose when there's a problem, right? When I told you that customer called and she's like, well, it's got to be the spark plug. And I'm kind of like, no, that needs diagnosis. Like, you're just guessing. You know, that's like going to the doctor. The doctor doesn't do any tests and just starts prescribing medications. Like, no, that's that's the same as the mobile mechanic. I think his name might have been Mo, you know, Mo the mechanic, right? So when you want to really diagnose this, you need to be able to take some measurements, okay? But when we're on that coil unplug, for example, which we're going to favor coil unplug because that's pretty much what everything is now. It's been that for a little while. You can measure the primary voltage, but it's very hard to measure the secondary voltage because it's all shoved down in the coil. Like, so if we look at this picture back here, the secondary is down here. Well, if you look at this picture way back, that's down in the engine. How are you going to measure that? Like, you can't touch it. It'd be nice to be able to measure it, but generally you really can't, right? So when we start to do some of this more diagnosis, we may use something like a wand, or some sort of an attachment to a picoscope that's going to measure it through induction, right? You can't physically probe onto it, but you can kind of measure it through induction, just the same way that the primary induces into the secondary. Your secondary can induce some into your wand, and you can then track what the voltage is doing on the secondary, right? So when we go to do these diagnoses, just remember, induction goes beyond primary to secondary. We use induction to charge our phone. We also use induction to do the diagnosis of the system. Okay, so that's the first lesson. Second lesson, the coil is a step-up transformer, right? So what happens in one winding will happen in the other. So sometimes when we want to know what's wrong with it, we may probe the primary, and a good picture of the primary will give us a good picture of what's happening in the secondary. Make sense? But you understand the secondary is high voltage. You can't put your DMM on that. Your DMM's not that. Your DMM's rated for 600 volts. If you're talking about 40,000, the DMM is not going to survive that. Make sense? So if you do want to measure the secondary, you got to look into some things like this. But most of the time, we'll measure the primary, because what happens in the primary happens in secondary. So if the secondary's got an issue, we can see it in the primary. If the primary's got an issue, we could see it in the secondary. Now, you guys remember that math calculation we did, right? 12 volts became 12,000 at 0.005 amps. What if I was only getting 9 volts to the coil? What's that going to mean the secondary voltage is going to be? Like, how much? It was 12 volts to 12,000. If it's only getting 9 volts on the primary, it's going to be 9,000. If we needed 12,000 to jump the spark plug gap and you only got 9,000, it's not going to jump the spark plug gap. What do you got? No, a misfire, at least, no spark. Yeah, if you got that on all the coils, then yes, exactly. It depends on the system, but kind of the point is, if you have low voltage making it to the primary because you have a primary wire chewed, guess what? You got low voltage on the secondary, not sparking the spark plug. Make sense? So again, when she sent me the picture of the primary wires chewed, and I knew that the code was for a primary circuit, it's like, duh, fix the primary. The primary controls the secondary. And I'm looking at chewed wires in the picture of the primary. Forget about the spark plug. The spark plug's on the secondary. The spark plug probably is not sparking. I agree. But it's not sparking because it's not getting the correct voltage from the primary because the wire's chewed, dude. Duh. Okay, makes sense? So as we continue, the primary circuit's characteristic transfer into the secondary due to mutual inductance. So again, whatever's on the primary is on the secondary, whatever's on the secondary is on the primary. Cool. Just different numbers, but the same shape when we look at a waveform. And so with induction, part of the reason we get a little bit more into this is we also use induction for a reluctor spinning and the teeth interacting with the stator. So when we start to want to control the coil, we need to know where the engine's at. So we're going to use a type of sensor that uses induction, and we will come to that one. So if we had a little spinning reluctor, so that's like a toothed wheel spinning around, that can induce electrical flow into a sensor. That sensor can then give a signal to the computer, and the computer can know exactly where it's at. That also uses induction. So that's why I wanted to pick it. Cool. All right. And then additionally, when we're talking about that, when the stator tooth approaches the magnet, it reduces the reluctance near the field, pulling the magnetic field out of position, exciting the coil, and generating a positive voltage. So you're like, what? Let me just give you a preview. You see this waveform? It had negative. It started to go up and up and up, and then it dropped away. That's as this tooth right here gets closer to that sensor. So this sensor right here is going to give a signal to a little module. So this is like, a lot of times we'll call this an ignition pickup. All right. So if we go into the first type of distributors, those don't even have a pickup. They don't have any of this induction. They actually use breaker points. We'll get there. That's going to make a connection and break a connection. But the problem with those they make and break over and over until they fail. So we get away from that and we go more into this induction. This really shouldn't fail because those are never actually touching, right? This tooth just goes by that sensor. And when it does, it induces a major voltage, right? So this is each one of the teeth. Tooth 1, tooth 2, tooth 3, tooth 4. 1, 2, 3, 4. Round and round. And this is mostly just relating to induction for now. So it's mostly to make sure you understand, because there's magnetism in place, it can induce, remember how it makes a magnetic field? The magnetic field can induce voltage into the circuit. Well, it does. This is going to be a magnetic sensor, and these are going to be iron, a ferrous type of a tooth, which means it's magnetic. It's got a magnetic field. Like a magnet is not attracted to aluminum because it's non-ferrous. A magnet is attracted to steel because it's ferrous. It's got iron in it. Okay, so that's what we got here. A magnetic type of sensor and a ferrous toothed wheel. This, for example, is like a reluctor. So right back here, we're talking about the reluctor. As the reluctor spins, the teeth interact with the stator. The stator is like the sensor in this case. As this spins, it'll react and the magnetic field will induce a voltage. Cool. The reason that we're covering this right now is because all this is occurring on the primary side, and we can use it in several different ways. So when we start covering the different types, you'll be like, oh yeah, I kind of understand. That's not physically touching. It's just inducing. Cool. Which is also why it doesn't wear out. Okay. And then from there, this ignition module right here is going to be watching this. So this ignition module is looking at this waveform being like, oh yeah, hey, that tooth just got very close. It got as close as it's going to be. That means it's time to fire the spark plug. And so this ignition module will actually be charging the coil and then take the ground away from the coil, and that will induce the primary to the secondary, and that'll make the chispa, right? The chispa, the little spark. Okay, but if it's a big coil, that'll make the rayo, the lightning. Okay, cool. So that's the idea. Now talking about induction on a more modern system, we could use something as old as this, or we could use a sensor that uses a similar induction and send that to like an ECM. And the ECM can then control the coils individually. Okay, and I'll show you that. The sensor will literally just be like an input to the ECM, and the ECM could actually have its own ignition control module. So if we look right here, this was a standalone ignition control module, but now for the most part, we build it into the ECM. Sometimes it's its own chip in the ECM, but you can't replace it, so it's part of it, right? So if we have a big ECM that's doing a lot of work, we're not so different than this, except this sensor was an input to just the ignition control module. Now we put the ignition control module in here, and we put a similar type of sensor, and it induces, and the ECM is like, oh yeah, I know where you're at. The tooth just passed, and we're waiting for the next tooth, right? So we're still using induction. That's kind of my point. This is old school, but we're still using induction on some that's computer controlled and fuel injection and everything. All right, so as we get into the primary, and we're going to go back and forth a little between primary, secondary. The PCM in a new car, the PCM, so the powertrain control module, is going to determine when to fire the coil based on system voltage, coil temperature, engine RPM, and this is key, other input sensor data. So, in fact, somebody asked me on YouTube literally yesterday, one of the discussions you guys are going to do later is how to set ignition timing. When we go to set ignition timing, we're really setting the base ignition timing, And then the computer is going to take over and do the advancing and the retarding as needed. As needed based on all this, and especially sensor data. So in the later half, we talk a lot about sensors, and I just need to make sure you understand the reason we include sensors in ignition is because that sensor information is going to help the PCM determine when to fire the coil. That's the timing. And we could do quite a few different methods, but that's all on the primary side of the ignition, right? The primary side is controlling the coil. It's the smaller wires. The secondary side, that's a little different. Cool. And then one of the goals is to begin the dwell period soon enough in advance of the spark so that the coil's primary current flow is sustained enough to fully saturate the coil, which will make it reach its full energy potential. You're like, what? All right. The coil, if I were to remind you back here, do you guys remember the ramp? This is your coil ramping up. It takes time to completely charge that coil up, right? So we basically give 12 volts in ground to the coil, and then we wait a little bit. And if we wait long enough, it'll reach its full potential, just like all of you. If you study long enough and hard enough, you'll reach your full potential. But if you don't put in the time, you're not going to reach your potential, right? Same with the coil. So that amount of time is called the dwell, okay? We don't usually use the dwell as so much of a term now, but if it's old school and you're talking about like old hot rods and you used to be able to adjust the dwell, like there are some adjustments you could do. The dwell is just that ramp up time. So if we start it soon enough and we leave it dwelling, that means giving it 12 volts in ground. That means the ground is connected. If we let it dwell long enough, it'll reach its full potential. Now, there's a couple reasons that that's important. That means we need to very quickly close that ground and let it start to charge up and increase the dwell time. But it takes time to close it. So we've gone mostly to computer control. The computer can close the circuit much quicker than like a physical contactor, okay? And then I'll do some current limiting. And so when we get into induction again, here, let's say that this is the primary coil. There's an interesting thing that happens. The primary coil has, just a few windings, but what's interesting is when we send current through it, the current is going to cause a magnetic field. And each of these little circles down here is additional induction. It sounds kind of weird, but like what you could basically say is if you have the coil going around and around and around and around, this almost gives it like in additional induced voltage. Cool. So let's say that we give that coil 12 volts. Well, just because it's wrapped around in circles and it's making a magnetic field, it can induce that voltage and transfer it into the secondary winding. So it's kind of weird. We might only have 12 volts going through this wire, but these round and round of magnetic fields can induce the voltage even more. Kind of strange, huh? But it's part of their design. All right. And when we get to the point where we want to fire the spark plug, what we're going to do is disconnect the negative end of that. And all these magnetic fields, these are all going to collapse. And there's going to be that collapse of magnetic field is going to force all this energy to be transferred over to the secondary through induction. Okay. And that's what we get into right here. So if you look at this, this is more like your primary. So here's your battery. Your battery goes to your ignition switch. Your ignition switch is going to go to this pickup. And if we're giving 12 volts to this pickup, as this is going to go around, it's going to end up either like it'll be connected and that'll charge the coil. And then when we disconnect it, see the little cutout right there? It's kind of small. But when we disconnect it, that's going to take away, in this case, the 12 volts. That's actually going to like cause a collapse in there. So when we're looking at this is how we can determine the engine's position, basically. All right. Now, if we were to look at it with the primary and the secondary, we're going to give it 12 volts. We're going to send it through some sort of a pickup. And the main purpose of the pickup is going to be to let it get connection, 12 volts and ground, which is going to be the dwell. It's going to charge the coil, right? So while it's charging the coil, 12 volts is going through. It's making a magnetic field. But then if we open it, all of a sudden, this magnetic field is going to induce the energy into the secondary, which is going to be at much higher voltage. And what do you think that's going to do? You know what voltage wants to find its way to, right? It's trying to find the path to where?
Ground.
Yeah, ground. Do you know where ground is on the secondary? It's at the other end of the spark plug, right? So at that electrode, that goes over to the threads, and those threads are contacting the cylinder head, which is like the engine block. So that's all grounded. So if we induce high voltage into the secondary coil, it's going to be like, hey, you know what? I'm going to find my way to ground, and I've got 40,000 volts of pressure to do so. It's willing to literally go through the spark plug and jump an 1/8 inch gap to where that ground is connected. Okay, so that's the whole goal. Typically, though, we're not really turning the positive on and off. We're turning the negative, but this is just like a visual so you know, right? We'll switch it on and off. So essentially what we're doing is we're switching the primary on for a period to charge the coil, and then we're switching it off to jump the magnetic field, induce it into high voltage, have the high voltage go through the secondary circuit, down the spark plug, and jump the gap and make the spark. Okay? It's not that complicated, I think. If you were to look at it a little bit zoomed in, here's what we got. Let's get 12 volts going right here to the primary winding. Remember, this primary winding doesn't have that many rounds, right? And then it's going to go to the switching terminal. What the heck is the switching terminal? Well, it depends. That's why we have to cover some of the different systems. The switching terminal is what's going to control the dwell. So if it's closed, this is charging up. But when we open it, it stops charging, right? That's the resistance increases, and so there's no more current flow. When there's no more current flow, this magnetic field is going to collapse. It's going to jump right over into here, all right? So let's say we close this switch, charges the coil up, charges the coil. Hopefully we can keep it closed long enough to reach its full potential. And then when we open it up, the magnetic field collapses, it jumps into the secondary winding as much higher voltage, right? And so if this is all positive 40,000 volts, it's going to be going down to the spark plugs. All right, but so the left side of this is your primary and the right side of this is your secondary, in case you can't tell. So if I were to say primary side is low voltage, what is the secondary side? High voltage, bingo. So when we look at the HT terminal, high tension means high voltage. You guys seen spark plug wires? You ever notice they're really fat? You ever cut them in half and realize almost all of that's insulation and there's only a tiny little wire inside? Kind of funny. Why do you think there's so much insulation? Close, you're getting there. You're getting there. Yes, exactly. So if this has 40,000 volts, that's enough to jump through a regular primary wire, that little tiny rubberized insulation. Oh, it'd jump right through that in a heartbeat. No hesitation. No, like you guys like coyotes? You put a 6-foot fence and you think it's going to keep the coyotes out? It won't even slow them down. Those coyotes, they could do 10 feet. They could jump a 10-foot fence as long as they can get a small run on it. Like that high voltage wouldn't even be slowed down by a 6-foot fence. Wouldn't even be slowed down by normal insulation. That's why the insulation's super thick, because this is all high voltage. That's also part of the reason that when our spark plug wires, get a little bit worn and dried out, all of a sudden, like if it's a little wet out that day, they might start to arc out of the side and you'll get a misfire when it's wet. You'll run it through the car wash and it won't start. And then when it dries off, it will start. That's probably because that water being on the secondary ignition insulation allows the path to ground a little easier. And rather than jump the spark plug gap, it's like, you know what? I found an easier path to ground. Right out the side of the wire, straight to the valve cover. Tick, 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 tick. You'll pressure wash it and you'll start to hear it crackling and little zapping and stuff. That's all secondary ignition problems. And it does happen. Okay. So if you look at the coil again, we've got, generally it looks a little bit more like this. The primary in blue, the secondary in red. We'll a lot of times wrap them kind of one around the other. So if we send the 12 volts and ground through the primary, it charges it. Then we take the ground away. That magnetic field will be induced into the red, which look, the red is the secondary. It goes down to the spark plug, right? And the amount of coils kind of depend. And the details of the shape can kind of depend. But when you're thinking about the secondary coil literally ends at the spark plug. It goes through the boot or through the spark plug wire or whatever down to the spark plug. Okay. Pretty interesting. Cool. And they have the book goes into some detail about how the coil is constructed. And, sometimes we use like a laminated frame, and we could do a lot of different styles. So this coil, this is the frame, and then it would have the coil right here. It'd be round. Or this is an old school coil. This is a canister coil. So this is if it's an older car, this right here is the coil. If it's a newer car, it's probably more going to look like this. In fact, this really isn't that new. Everything new is now going to be coil unplugged, but coils did look like this. Then they started building on this frame, and then they started looking like that. And then they started looking like this. So who's ever heard the term coil pack? Coil pack was kind of like multiple coils in one housing, right? So if you look at this one, how many spots are there for the spark plug wires? 2. So that's a coil pack. It does 2 cylinders. So the way that I look at it was like back in the day, we had the distributor and we had one coil. It looked like this. And that coil, that coil could fail, right? When that coil failed, it was kind of expensive, wouldn't you think? So the customer's like, what? I need a coil and it's $30. Imagine telling that customer, hey, we're going to go away from one coil and we're going to put 8 coils on your V8. They'd be like, what? I'm not buying it then. Right? So we didn't go from 1 to 8. We went from like 1 to maybe still 1, but a bunch of coils in a pack, or maybe this one does 2 cylinders at once. So you could get away with just 4 of these rather than 8 of them, right? But it's been a progression. And now you're at 1 coil per cylinder. And there's a lot of benefits to that, but it does drive the price up. And that's just the way that things are going. Drives the price up, but it's more efficient. It's going to be easier for the ECM to control precisely. It's going to be a little better for emissions and fuel economy, right? Like the same things it always is, right? So we had a lot of types. The coil pack was just coils in packs. This did 2 cylinders. This did 2 here, 2 here, and 2 here. So this coil right here would actually control 6 different cylinders. I didn't love these, and the reason why was, if you see, it's still really 3 coils in one. If this coil was bad, you know what you had to replace? The whole thing. The whole thing. Whereas if it was this style, you could do 1 coil pack. Then, probably the other 2 might fail shortly behind it, but at least this one, if this coil was bad, this is cheaper than this whole entire thing. But they're both coil packs, right? Most of these are called a waste spark, and we get into waste spark a little bit. The waste spark is where they pair cylinders. 1 cylinder's on the exhaust stroke TDC and 1 cylinder's on the compression stroke TDC. It sparks both. One of the sparks is productive because it ignites the air fuel mixture and makes the power stroke. The other spark occurred on the exhaust stroke. That was kind of a waste spark, right? We'll come back to waste spark, but this is more like how the coils can look, okay? And then again, the coil, to step up voltage from the battery to kilovolts. Whoa, new term, hold up. Remember how we went from 12 volts to 12,000? How about I say we went from 12 volts to 12 kilovolts? That's the same number. 1,000 volts is kilovolts. Remember we talked about that? 1,000 grams is a kilogram. You're going to jail, right? Well, you're probably going to jail either way, but you're going to jail with intent to distribute or something because it's like kilovolts. That's way too much for just you. I mean, grams. Okay, same thing. One volt to 1 kilovolt is 1 to 1,000. 12 volts to 12 kilovolts is 12 volts to 12,000 volts. Cool. So that's kind of what I'm more saying. It goes from voltage of the battery, which is primary, and it bumps it up to thousands of volts. We typically measure the secondary system in kilovolts, right? So if I say it's a 40 kilovolt system, it's a 40,000 volt secondary ignition. It's 100 kV, 100,000 volts. That you're going to feel that one, let me tell you. Right, and then sometimes there's a simple transformer. Divorced means they're separate. It's like in two pieces. Married means that they're actually got continuity. So part of the reason that's important is when you go to test a coil, it would be kind of nice to just measure the primary windings. Like if you thought the primary windings were good, you could actually measure blue to blue and check the resistance. But sometimes they're divorced and sometimes they're together, and there might be continuity and there might not be. And so I don't really remember all the tests because there's so many different types. But if you're following service info and it tells you to measure, let's say it tells you to measure the secondary ignition coil, that might literally be from here to here. That's a good measurement, but that's only true about this coil. I'm not sure. This coil may have continuity between the secondary and the primary, but this one may or may not. I really don't know. So I'm regularly following service manual. That's part of the reason you need to follow the manual rather than just kind of wing it. Be like, oh yeah, you can measure primary to secondary and it should read this. I don't know that that's true. There's a lot of different types. Make sense? But typically, primary might be a half an ohm to about 1.5 ohms. That'd be pretty typical, which kind of makes sense. You're going to have like a kind of high amperage at a half an ohm to 1.5 ohms. But the secondary, 5,000 to 15,000, is that kind of interesting? Is there like do you notice anything in our finely tuned universe that there might be a proportion there? We go from 12 volts to 12,000 volts, but we also go from 0.5 ohms to 5,000 ohms. Like everything's proportional. Make sense? So you're going to do 10 times the voltage or 1,000 times the voltage at 1/10 of the resistance to maybe 1/1000th of the resistance. Depends on what you want to do, right? But it's always in proportion. It's not just random. Cool. And who figured this stuff out? Far smarter than me. Apparently, Watt, Mr. Thomas Watt, Watt's law. Okay, and we talked a little bit about the dwell. Remember, here's the dwell. When we have 12 volts in ground, the amount of time. This is the amount of time. It's ramping up. We can measure that from here to here. But the thing is, to measure it, you know this screen right here, this is actually on the oscilloscope. So if you wanted to measure the dwell time, you'd have to hook this up to the oscilloscope and physically graph it. And then you could determine how many milliseconds this is based on your settings and be like, oh yeah, it has this much dwell time. For example, if this is ramping up nicely. So that ramping up nicely tells me that primary side of the coil is working. I'm not going to set a primary circuit code because it's ramping up nicely. If I had a mouse chewed primary wire, do you think it would ramp up like this? No, because it's open. It's like if you have a chewed wire to the light bulb, is the light bulb going to light? No. That means if this coil is not getting the 12 volts in ground from the primary, it's not going to ramp this way. If it doesn't ramp this way, hey, you know that the problem's in the primary side of the circuit. You set a primary circuit code. You send that in a picture along with a chewed wire to some guy, and he says it's not the spark plug. How dare he? The spark plug would have no effect on this, right? So that's why when it's a primary code, we're like, let go of the spark plug. Just forget about spark plug. We're not worried about spark plug. It's a primary code. That means it's on the primary side. Okay, cool. Right here. It's not ramping right. And there's a few other ways that we could look at it, right? But right now we're going to really make sure we clarify the primary and secondary. Purpose of the primary, turn the primary circuit current flow on and off, okay? So if we want to control the spark, we need to turn the primary on and turn it off. That's this time right here. We turn it on right here. It dwells, it ramps up. And then you know what we do right here? Turn it off. And then that's going to create on the blue line, boom, this spike in voltage. That's actually the firing. We'll talk about this waveform a little bit more. This is where the primary is controlling the secondary. Cool. All right. Again, the opening and closing of the primary is what's going to create the voltage surge necessary to ignite the combustible air fuel mixture. Does that make sense? If we give it the dwell time and we charge it up and then we rip the ground away, that's going to collapse the magnetic field, induce it into the secondary, send the spark down the spark plug wire, spark the spark plug, light the sucker on fire. And then you can have your power stroke. But if anything goes wrong before that point, you don't have any spark. Now, why don't you have spark? Again, that's kind of why we're covering all this, and we get more into the diag next time. If we had a good primary charge up, but it didn't make spark, then I might look at that spark plug, potentially, sure. And FYI, if the spark plug has a lot of resistance on it, this line will actually be a lot higher. It'll take more kilovolts to arc that gap because the gap is open or because the spark plug is maybe really fouled with carbon or something. So like it's really exactly. We could say maybe it's open too much, but if you're really picking up what I'm putting down, we could scope this out and the height of this line can tell us if there's a problem like that. Rather than tell the customer you need to put spark plugs in it, right? We can actually measure it. Now, is the customer going to want us to spend all the time doing all these measurements and stuff? They're going to be like, AutoZone does free diagnostics, remember? I'll be like, yeah, we got to hook up the oscilloscope on that and check your firing line and see if it's too high. Make sense? So like, we'll come back to that a little bit, but this waveform right here is actually monitoring the voltage, and the voltage is going to tell us a lot. Cool. All right. And then basically what we're saying, the primary circuit is actually controlled by grounding. The ground of the coil is the controlled one. Remember in the beginning, I showed you were pulsing the positive. That's not, maybe they used to do some of that, but in reality, when you turn on the ignition, you're turning on the 12 volts to the coil and it keeps it the whole time. Then what happens when you start to crank it over, it gives it ground, but then it takes it away. And when it takes it away, you tell me back, what's that do? When it takes the ground away, what's it do? True, but like we needed to take the ground away. Shanana's fun. But if you remember back here, remember right here, we give it 12 volts and we let it keep 12 volts and that ramps it up. But then when we take the ground away, exactly, it collapses the magnetic field. It jumps over here and it makes the spark. Correct. So we need, like it's saying here, we need that ground to be controlled. What controls it though really depends on what type of ignition system it is. So we're talking a lot about in general, and then in the end, we're going to like start nailing it down. This is how this system does it. This is how this system does it. This is how this system does it. But you know what they all do? They all give it 12 volts and pulse the ground to start the spark. Okay. Give it ground for a while to charge it up, take the ground away, poof, and make the spark. Cool. And then again, what's it say right here? When the coil is being grounded and turned on, it will be saturating, so that's building a strong magnetic force. What is that amount of time called? The dwell. Bingo, got it. The dwell. And then when the ground is removed, the coil is turned off and will fire. Cool. And will fire. So that's the spark right there. And so then again, we're talking about the dwell time. And sometimes they'll measure dwell in degrees, right? Because if they measure it in milliseconds, It's going to change with engine RPM. So sometimes it makes more sense to measure it in degrees. Cool. So look right here. This is a little bit more of a modern system. Um, and it's, this is one way to do it. We've got the ECM. The ECM is controlling the ignition module. The ignition module is referencing a magnetic triggering device. What do you think the magnetic triggering device is? Like the key turns on the power. So no, the magnetic triggering device is something, it's going to spin. Yeah, it's in the distributor on the older system, but on this one, I don't know. I can't tell if it's a distributor type or not. It looks like it could be, but either way, this is what's going to tell you where the engine's speed and location is, right? It could be a crank or cam position. Yep, it's true. On an old school car, they didn't exactly have crank and cam. They had just like a ignition pickup, and the pickup would pick up where the engine was and then send a little signal. So remember how this comes around and it's induced? You know, we could put some magnets, a magnetic sensor on there and some points, some ferrous metal points on the tooth on the reluctor. Either way, the ignition module needs to get a reference. It needs to know where the engine's position is and how fast it's turning, right? Then from there, it can fire these coils, right? It is in the distributor on the old ones. Yeah. But then when the distributor's gone, it becomes the crank and cam sensors. Yep. So this is going to give an input to the module. And then as a result, the module is going to say, all right, let me charge this coil up and then let me take it away. And when it takes it away, it's going to induce high voltage into the secondary and fire the coils. This one's actually a waste spark. You know how I know? 2 coils per cylinder. That'd be a waste spark system, pretty much guarantee it. Yeah, because if you look, how many cylinders are there? 1, 2, 3, 4. There's 6 cylinders, but there's only 3 coils, which means that coil's firing twice. One of the sparks is on exhaust and one of the sparks is on compression, which is where we really need it. So one of them's wasted. That's a waste spark right there. But either way, do you guys understand what's controlling the coil? The ignition module powers it and then unpowers it, which causes the spark. And how does the ignition module know? It references the triggering device, right? Which could be a pickup in this case. So let's look at what the primary is. This is all the primary. Everything to the left of the coil is considered the primary. Now it depends on how far you want to reach, but generally, I would say the ignition module and the wires, the small wires that go to the coil, are definitely primary. But additionally, the coil inside of the ignition coil, that's the low voltage, that's also part of the primary, right? So half of the coil, ignition coil, is the primary. These small wires are the primary. You might even go as far as to say the ignition module is the primary because that's the switching device. It's giving ground and taking ground away. In this drawing, it's actually giving voltage and taking voltage away, which is, it's old school. It's a little abnormal. But some would even go to say the magnetic triggering device would be part of the primary because in a way that's all what's controlling it. Yeah. But I tend to not really think of it that way. I think that is a little bit more of the triggering part. So the trigger is this pickup sending a signal to this ignition control module, and the ignition control module is making the connection and taking the connection. So you can kind of look at it either way. It's like if you want to lump them together, it's all part of the primary, and the primary includes the trigger. But sometimes it helps to separate them because if you've got a primary code, you're really dealing with like from here to here. But let's just say we had a problem on this wire of the triggering device. Which coil you think would be affected? All of them. And that's why I'd say like you might separate them. If you got a primary issue going to this coil, it's going to affect these 2 spark plugs. Whereas if you've got an issue with the triggering, And it's going to be more like all the spark plugs, right? But either way, it's all on the low voltage side. You could consider it all part of the primary roughly, and a sub part is the triggering. All right, cool. How about who thinks they know where the secondary's at? Yeah, on this picture. Yeah, exactly. The spark plug is secondary. That high tension cable, aka spark plug wire, is secondary. And the part of the coil that's got a lot of windings, that's the secondary. Make sense? So the primary induces into the secondary, and from there on out, it's all secondary. That's all going to be high voltage. That's all going to be 40,000 volts. So if you think of the spark plug's 40,000 volts, the spark plug wire is 40,000 volts, and half of the coil, of the ignition coil, is 40,000 volts, but it's the secondary half, right? Remember that car I told you about? Customer called and they had a primary ignition circuit code. Do you understand now? I was saying, like, forget the spark plug, don't bring the spark plug up again. It's a primary ignition circuit code. She's very fixated on the secondary spark plug. If it's a primary, that means it's between here. Well, that means it's between here and here. We're not worried about the secondary side. Get what I'm saying? Got to have the primary working to even have the secondary trying to work. Cool. So primary and secondary, you guys should be pretty good. One thing I like to make sure you understand is, remember, the secondary circuit does include one half of the ignition coil. Okay. And then again, 20,000 volts, 40,000 volts, 60, seen 100. The exact voltage is going to vary depending on the engineer that designed the system. And if it's a very, very high voltage from the factory, it's probably a performance car. Probably going to be running some kind of boost, some high compression, some kind of race car stuff. Cool. And then again, just remember, if you really wanted to expand the primary, technically the primary starts at the battery. Right. The reason I like to say that is because remember, we talked about how the coil is a transformer. It takes whatever voltage it can get and it steps it up. What if your battery is low? What if your alternator is not charging properly? What if you're, let's just say for whatever reason, you're expecting to run 13.9 volts while you're running, but your alternator kicks the bucket and now your battery voltage is down to 10.9. Why is that going to have such an effect on your ignition? Close. The dwell time could be the same, but it will try, but it has a limit. If you only have 11.9 volts and you were expecting to have 13.9, that lower primary voltage is going to be equal to a lower secondary voltage. So like, for example, my motorcycle's charging system has failed on more than one occasion on several different bikes. Motorcycles don't have an alternator. They have a stator and a regulator rectifier, but let's just call it an alternator for now. When my alternator failed, the reason I don't have any kind of charging light or anything. It's a motorcycle, so there's not really a lot of warning lights. You just ride the thing. All right. So as I'm going, all of a sudden I come around a turn, and I specifically remember where it was. I got off the 215 back when I was working third shift, and I punched it on the 74, and it just stumbled. It was just kind of like, blah, 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 blah. And the more gas I gave it, the more it was stumbling. And I was like, that's weird. And then the other thing was, it's in the wintertime and I wear a heated jacket. So now you can call me soft if you want, but that heated jacket pulls a lot of battery voltage. So when it stumbled, I was kind of like, I was thinking about all these things, and I've had the alternator type of part fail before. And I was like, you know what? I wonder if I'm not charging. So I disconnected my heated jacket, boom, and I punched it again, and it had quite a bit more power. So if my heated jacket is pulling the battery voltage down because the alternator is failing, and I disconnect it, the voltage would jump up a little bit, right? And it actually ran a little better. So I was kind of like, ooh, my system voltage is down. That means the primary voltage is less. That means the secondary voltage is less. And under high throttle acceleration, it needs very high secondary ignition voltage, and it didn't have it. So it's kind of like, all right, time to like I just kind of tucked behind the windshield and I barely accelerated and I just barely made it home. Literally, it died pulling into my driveway. And then what do you think? What do you think happened when I went to restart it? Totally dead. No, it wouldn't even crank. Yeah. So basically, when your alternators failed, you're just running your system off the battery. When your alternator's running, you're going to get your 13.9, your 14.2, your ignition's happy. But when your alternator fails, your battery voltage is dwindling. Your primary voltage is going down just along with your battery, right? So just got to think the primary voltage is all tied into your battery, your alternator, all that type of stuff. So if you got a battery alternator issue, I agree that could cause ignition problems. But think about it. If your system voltage was low, would it cause a misfire on one cylinder? No, it would cause it on all of them. So that's one of the reasons I like for you to understand the system a little more overall. Because again, if you jump on the forums and they're like, "Oh, you got a misfire?" Yep, definitely check the battery. And it's sort of like, well, 5 cylinders are working fine and one is not working fine. Like, yeah, technically the battery's kind of part of the primary, but like part of the primary for all 6 cylinders, not one. See what I mean? So I wouldn't waste a whole lot of time on that. All right, cool. Very good. And then when we're looking at the primary, okay, we're going to look at a few things here. And and we may jump around a little bit, but this line right here is going to tell me a lot of things, okay? So if our primary voltage is low, I could actually see that on this line. If our firing line is high, I could see that on this line. This is actually showing the coil oscillations from when it's reconnecting, right? Technically right here to right here is the amount of time that it's burning. Like all these can indicate problems. And so that's mostly for next time where we talk about actually taking these samples, which means we get the oscilloscope out, we probe it into the primary side, and we're actually going to set up the correct voltage range and time interval and take this reading. And this could tell us all about the ignition system, all about it. But you got to have a good overall understanding before you even know how to start to interpret this. So we will look at this one more time, okay? And then again, it's just it's very very important when we look at the amount of voltage. So like if we're under very heavy throttle, we might need 15 kilovolts to actually jump that gap if you're under wide open. But if you're on less throttle, you might only need 10, right? So if you have a bad primary voltage, it might actually do okay at idle and light throttle. But when you blast it and you're wide open throttle and your cylinder pressure is higher, you need more voltage. What if the coil can't generate more voltage? It's not going to be able to spark the gap. It's not going to be able to arc the gap, right? So one of the big takeaways here is the higher cylinder pressure you have, because wide open throttle, because of turbo, because of supercharger, because of high compression race car stuff, you need more available kilovolts to jump the gap, but you need a coil to be able to produce that. So if the coil's starting to fail and it can only make 10 kilovolts, it's not gonna spark at higher RPM. That's when you get a car where you're accelerating hard, and when you accelerate hard, it starts to break up and fumble and bumble and blah, 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 blah. But then at idle, it's decent. So it's really common when you got a failing coil. It might sound decent at idle, but if you power brake it, gas and brake, and give it a little gas, all of a sudden it's like boom, 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 and you're like, huh, that's kind of interesting. There's more demand on that coil with more engine load. Okay, makes sense? Just log that in the brain. Unfortunately, there's also more demand on the fuel injectors and the fuel system under wide open load. So if you got out there and you punched it wide open and it fell on its face, it could be ignition, but it could also be fuel because more acceleration demands both better, higher voltage and more fuel. Yeah, so you could, you know, when you go to try to do some of these tests, like the next thing we cover is fuel systems. You just got to know, unfortunately, just driving it won't tell you if it's ignition or fuel for sure. Typically, if it's a fuel thing, you know, it's more like a consistent loss of power. Whereas if it's one coil on a coil on plug system, it'd be more like a misfire. But if it's a car that has one coil for all the cylinders, the ignition coil failing will just be a sluggish and the fuel will be a sluggish. And it's hard to tell which one's which, to be honest. So driving it a lot of times is not enough for you to determine. You're going to have to take some measurements, do some actual diagnosis. Cool. All right. So this goes into firing voltage a little bit more, but I think for now you guys are probably pretty good. And then just summarizes like on the different systems, the primary, battery, ignition switch, a ballast resistor, which is on the old school, the ignition coil, old school, yeah, ballast on the old style one, yeah, condenser. Ignition, if we look at ignition coil, primary winding, let's come back to that. A capacitor, breaker points, that's old school. I'll show you some breaker points. The ignition coil, oh, here we go, pause right there. Now on the secondary, ignition coil secondary winding, coil wire, distributor cap, rotor, spark plug wires, and the spark plugs. Wait a minute, is the coil primary or secondary? Well, it's primary here. And, oh, it's both, exactly. One half of it is the primary winding, and the other half of it is the secondary winding. Okay, so just that's the one thing that's both, right? The primary is the low voltage side, the secondary is the high voltage side, but they're both technically part of the coil, so therefore it's primary and secondary. Let me know how that works out for you. Yeah, just let me know how that works out. All right, and this was more like on a distributor system with breaker points. Okay, if we went with a distributor system that was electronic ignition, we get rid of the breaker points, and so you can see the difference. Like let's go battery to battery, ignition switch to ignition switch. That's all primary. Ballast resistor is gone. Ignition coil primary winding, ignition coil primary winding. Capacitor breaker points, those are gone. We've got instead an ignition module and a triggering device. Okay, but so that's kind of what I said. Your primary and your secondary parts, they're going to vary depending on what type. So these are both distributor systems, but this is with breaker points and this is with an electronic ignition, which means it has the ignition module. And the ignition module, remember how it has the triggering device, which tells it when to open and close? Well, on the old school, the contact breaker points, I'm going to show you a picture of that. That was a physical connection. Close would charge the coil for an amount of time called dwell. Open it, which would initiate the firing.
So they kind of went away from the physical because a lot faster.
Faster, true, but also if you have a contactor that opens and closes every time the spark plug fires, it would wear out. Yeah, so back in the day, we used to do a lot of tune-ups. Yeah, you need points, condenser, spark plug wires, cap, and rotor, and you need it every 12,000 miles. Every year, we're going to do a tune-up, right? So we're right at the essence of why we don't call it a tune-up anymore. Tune-ups were needed so regularly because those contact breaker points were failing, the cap and the rotor were failing, right? Then they did get a little bit better when we got rid of the breaker points, but you still had some of this stuff on the secondary. So if we look at the secondary, the coil, that's the same. Coil wire, that's the same. Distributor cap, that's the same. Rotor, spark plug wire, wait, it's the same. So on this system, this needed a lot of tune-ups, especially because the breaker points. And then when they went to electronic, it was faster. We could control it. We could electronically advance and retard the timing, but also at least the breaker points weren't on there to fail all the time. So we went with that triggering device that, remember, if we looked at the triggering device way back here, there's no contact here. It's just through induction. Induction doesn't wear stuff out. Making something open and close over and over and physically move is going to wear stuff out. So when it's induction like that, it's just going to be much less of a wear item, much more reliable over time, but harder to diagnose. So when it was breaker points, you'd look at them and you'd be like, they're closed, they're open. They're closed, they're open. Oh, the gap is too big. Let me tighten it up a little bit. Oh, the gap is too small. Let me loosen it up a little bit, right? So my dad would tell me these stories. Oh yeah, I used to adjust that on my 1970 Jeep Wagoneer. I fixed it in the middle of the woods with nothing but my matchbook and a screwdriver. And I was always like, how? Well, because when you'd go to set the breaker points, there was a spec of how wide it should be. And it happened to be apparently, I guess, the same as a matchbook. So he'd use his little matchbook with the flint thing and sand them down a little bit to clean the corrosion, then tighten them up against the matchbook and then pull it out and it would fire up. And then it's old school, like it's fun, it's hot roddy, it's the greaser dog, it's the slick hair with the rolled up shirt, and all you needed was the matchbook and the screwdriver, and you could do the fix, and then you could whip your hair back. I don't have hair, but if I did, that's what we were doing. But you could physically see it and you could physically adjust it and you were good. Then when they went to this, the triggering device, like, what are you going to do with the matchbook there? Nothing. Put it away. You need to actually measure that. You need to measure if the voltage is being induced into this sensor. So you're going to really quickly whip your meter out of your back pocket. That's not going to attract anybody. Then be like, put that away, nerdy dude. But like, see, the matchbook was cool, but the meter's not cool, huh? That's what I'm saying. But you can charge more money with the meter, so I'm gonna take that. All right, and so that's been kind of the change. I think one more probe for the electronic control. Remember, the secondary ignition system is responsible for creating and delivering the high voltage required, especially when it's under pressure, it's more demanding. So the high voltage being generated by an inductive discharge of high voltage transformer, which is the coil. Electronic ignition systems eliminate the distributor, the cap, the rotor, the spark plug wires. Wait a minute, we're getting rid of all that stuff. Do you see the trend? So if we get into like a full-on electronic ignition, you don't have, not only do you not have the breaker points, you don't have the cap, the rotor, a lot of the spinning stuff, that's all gone. Now, why do you think that was the direction we're going? It's better for emissions. We can control it more precisely, yes, but also you think that it's going to be cheaper because you don't need to do tune-ups at 12K. So back here, used to be doing these tune-ups. These tune-ups were very often, but you use the matchbook and you look good. These tune-ups were still pretty often, but you didn't look as cool with the matchbook. And then we went to electronic ignition and it was like all that stuff is gone. You pop the hood and you don't see a distributor anymore. You actually just see the coil like this, and you're like, what the heck? Where do I put my matchbook on that thing? There's no matchbook, there's no spinning parts, there's no rotor, there's none of that. There's really no tune-up parts. Now, yes, we still have ignition, we still have high tension cables, in other words, spark plug wires. So we do spark plugs and we do wires, but like not as often. Maybe 3 years or maybe 5 years. Not like we used to 1 year, 12,000 miles. Those were the days, let me tell you. All right, so that's kind of the trend. They changed a lot. I think I got a little ahead of myself. Okay, right there. We've eliminated a lot of that and gone to distributor list. So that's a new term. Distributor list means there's no distributor. That's it. And I'll show you a picture of a distributor. Or it could be waste spark. So distributor lists and waste spark are kind of the same. It's just waste spark uses one coil per 2 cylinders and it wastes one of the sparks. Distributor list is just in general saying like it doesn't have any of the spinning parts, but it may have one coil per cylinder rather than one coil per 2 cylinders wasting a spark. Okay. But otherwise, we pretty much diagnose these the same. All right, cool. So when we get into the triggering systems, again, looking into this, there's a lot of things that can be said about how this line and how this waveform can tell us what's wrong, right? And so when we're making this waveform, this all has to do with the coil and how we trigger the coil and the condition of the coil. And the secondary side is more like over here. This is the primary, but what's happening in the combustion chamber is more over here. So that can tell us quite a bit. So if we look at some of these, let's just say transistor off, that's the points open. There's no current flowing. That'd be like the transistor off. There's no current flowing. See that right there? Number one. Number two, the coil saturation oscillations. Oscillations means up and down. That's going to occur during the initial turning on of the coil's primary circuit current flow, which is, let's think about that. When we connect that ground, that's going to start charging the coil, right? Interesting. Look at that. That's it. Its voltage is oscillating a little bit there. We're charging it, and there's going to be a little switch back and forth. So we had no connection right here. We made the connection. The coil's like, whoa, voltage. Okay, a little ups and downs. Cool. So this is the coil charging up. Okay. Then if we look at the firing line, the firing kilovolts, that's the voltage required to jump the spark plug gap and fire the spark plug. Ooh, interesting. So that's this one. So the coil charged up and charged up and charged up. Then we disconnected, right? We disconnected the ground on the primary. And what's that going to do to that magnetic field? What's that magnetic field going to cause? A big induction into the secondary. But the amount of volts is going to depend on the amount of resistance, right? If you have a lot of resistance, the voltage needs to be higher to overcome it. So give me an example of why there would be a lot of resistance in the secondary. Picture the secondary. The spark plug, yeah, if it's all coated with carbon, there's not a real clean ground. That's true. What if the spark plug wire's got corrosion on it? Anything that would cause resistance, or maybe it's got a bad connection. Maybe your spark plug wire didn't get clipped on all the way, right? Anything that would cause electrical resistance is going to cause this line to be a lot higher. Cool. So I remember on A8, there was 4 cylinders graphed, and cylinder number 2 had a really high firing line, and it was trying to say, like, what's wrong? You know, is it an injector? Is it low compression? Is it, you know, maybe low secondary voltage, or like a chewed wire to the primary? And it was like, no, if it's a high firing line, that's resistance in the secondary. That's going to be like corroded spark plug wire, a spark plug that's really fouled up and nasty, something like that, right? So the firing line right here, a high firing line means there's electrical resistance in the secondary. Cool. Then the next one was 5. The spark line shows the voltage required to maintain the spark across the spark plug gap. All right, take a look at that. So this is what it took to get the spark started. 5 is what it took to really like maintain it. Okay. And it's kind of, right? So 5 is also how long the spark occurs, right? So when you're looking at the initial boom, it's going to jump up, and then it's going to come down to a number and kind of settle, right? So 3 was really the firing line. I guess technically 4 is the amount of voltage that it was required to maintain the spark, right? It took a lot to get it started. It took a little bit less to maintain it. And then 5, as you'll see, oops, right here, that's actually the spark duration. The duration and shape of the spark are primarily results of resistance in the secondary circuit. So again, if you had high resistance, this would be really high, but this would also be higher too. Number 5 could be higher as well. And the duration is how long it occurs, but the higher it is, that's the higher voltage. So if you've got that corrosion, or you've got that fouling on the spark plug, 3 is going to be high, 4 is going to be high, and 5 is going to be high. Cool. So we're just evaluating that waveform. And then again, the coil oscillation is the remaining energy in the coil after the spark plug is fired. So if you notice, there's some oscillations right there, and then it's kind of smooth, and then it starts over here, and it's like there's no connection. Then boom, we make the connection. It charges and charges and dwells and dwells and dwells. Bang, we fire it. It took a lot to get it started. It drops a little bit to keep it started. It continues to make the spark for this amount of duration. And then all of a sudden we're done, and we close the coil again, or we open the coil. And this is this spark has dissipated the amount of energy that was in the secondary windings, but you might see a little oscillation as it's wiped out, and now you'll see it's a little lower. We switch the coil on, it charges it. We take the ground away, it fires it. Fire line drops. We continue burning. It's depleted. Okay, and round and round and round and round. Okay, not that bad, right? All right, and then when we talk about some of these next items, we're going to go into all the different types, but let's talk about timing. Do you guys know what timing means? It's like when the spark occurs relative to the location of the piston, though. So the timing chain is cam timing. Good observation. The timing chain controls when the valves open in relation to the piston. The ignition timing or the spark timing, that's talking about when the spark occurs in relation to the piston, right? Valve timing is valves with timing chain or belt. Ignition timing is spark, which could have been due to distributor rotation, or the computer is going to control it on the new stuff, okay? So when we talk about timing, it's when the spark plug fires relative to the location of the piston on the compression stroke. It's measured in degrees of rotation before top dead center. So if you think of it like this, let's make it pedaling a bicycle. All right. If you're pedaling a bike, your feet are like this, right? Let's say you look at your right foot and you're getting up to top dead center, right? Top dead center. And let's say you want to get a good, strong push of that pedal because you're trying to make maximum power going up this hill. Would you want to start right at TDC? Because by the time you think about it and you send a signal from your brain through your nerve to your muscle to contract, to push down, by then the pedal's already partway down, right? So you don't get a real thorough push on that pedal. So you know what we need to do? We need to start a little early, right? Top dead center is right at 12 o'clock. What if we started at like 10 degrees before top dead center? That way, by the time we're really pushing, we get like a full all the way down, a push down. That's why timing is always TDC. It's before top dead center. But how much before? Well, depends. You know, if you're going kind of slow, just a little before. But if you're like at red line, wide open throttle, your pedals are moving fast, that's the crankshaft, right? So here's your rod coming down. Here's your rod coming up. You'd want to start extra early, maybe 20 degrees before TDC, because you want to get a good push on it and you're moving fast, right? So how much degrees before TDC? I don't know. You know, the computer looks at a lot of things. But we do want to advance it more under heavy loads and under higher RPM. That's for sure. All right, so that's what timing is. As the timing, advancing the timing starts the spark generation earlier, which is going to allow the coil enough time to saturate and ignite the air-fuel ratio, air-fuel mixture at the peak of compression, right? So we want maximum pressure to be pretty much like just after TDC, when it can get a really good throw push. If you have the timing a little late, you're going to lose power, actually. If you have the timing too early, however, the piston's still going to be on its way up and you're going to be like spark and you're going to like try to push the pedals backwards. That's really hard on your engine. You can break some stuff. So if you over advance your timing, you can damage your engine, especially the rod bearings, because the crankshaft's pushing the rod up. The piston pushes the early combustion pushes the piston down, which pushes the rod down, and your poor little rod bearings like this, like pow, pow, like take that rod bearing. Again, every revolution it gets punched in the face. It's only so long before your rod bearing's like, you know what? I'm done with this. You know, so you might ruin that engine if you advance the timing too much. Cool. But if you don't advance it enough, you're losing power and your fuel economy is bad and your actually emissions is up, you know, so it's a fine-tuned control. Cool. So again, like when we talk about retarding the timing, these aren't my terms. These are the terms. You can take them or you can leave them. Just wait till you do manual transmissions and you talk about clutch parts. All right, but advancing the timing means it's early. Retarding the timing means it's late. That's it. It's that simple. It's not that the timing has a low IQ. It's that simply the timing is late. It's beyond, it's late schedule. It's supposed to be at 10 degrees before TDC, but instead it's only at 2 degrees before TDC. It's late to the party. That's it. Okay. And then maximizing the engine efficiency generally means we want the combustion process to be completed by 10 degrees after top dead center, right? So that means 10 degrees after top dead center, the combustion should have occurred. If we start it too late and we're not finishing until 20 degrees after top dead center, we're not going to get a very thorough combustion. It's not going to maximize our efficiency, and it's going to not have our lowest emissions possible. So that's why. Here's why and how. Let's say if it's a vehicle without a distributor, we're going to have some sensors. Those sensors are going to provide input to the ECM or the PCM. And the ECM or PCM is going to have complex programming tables and charts, timing tables, complex. This sensor reads that, this sensor reads this RPM is that, this RPM is that. You could do 28 degrees before top dead center, right? So it's very complex. There's a lot of different, it's a 3-dimensional timing chart if you really wanted to look at it. And that's written by the engineers from the factory. Okay. They've done all their research and dynoed and tuned it at this elevation and that elevation and this temperature and that temperature with this fuel and that fuel and the other fuel. And we're constantly trying to get it advanced as possible without causing damage. So if we could advance it to 39, and at 39, that was the most horsepower, why do you think that the manufacturer might only go to 36 degrees? Think of what I said. What if you start too early? You punch that rod bearing in the face. The manufacturers will be like, you know what? We think we can get 39, but 36 is pretty good. But the manufacturer is not going to do 20. So back in the day, the manufacturers were not really trying to advance the timing too much. They were going conservative because, the fuel economy standards were pretty low and the emissions requirements were pretty simple to meet. So like, we don't really need to run really high advanced timing. But as they tried to get better emissions and better fuel economy and still more power, now they're running pretty close to the absolute limit of what you can run for advanced emission timing. But have you guys ever heard of taking a car to the tuner, bone stock, tuning it and gaining 10 or 20 or 50 horsepower? Because that tuner will go through and actually break into the ECM and advance your timing even more. Now, if they over advance it, you'll damage the engine. But usually the manufacturer leaves a little margin where you could get a little more power out of it, a little more. Back in the day, they left a big old margin. You'd get a bunch more power out of it. But now they're taking most of that because they want the power, they want the fuel economy, and they want the better emissions, right? So on a non-distributor car, this is all, timing is all controlled with the computer, with the PCM. And it's very complex. Cool. But to control it well, we have to have a lot of inputs, right? So we'll have a crankshaft and a camshaft, and they've gotten more advanced and more precise and better over the years, right? So when we were talking about that ignition timing, remember, this is your piston, and it looks like it's just a little before top dead center, like 28 degrees before top dead center. That might be the perfect time to spark the spark plug, because this flame is going to take some time to actually travel and to combust and to reach maximum cylinder pressure to begin to push down. So we need to start it early. But if we start at 28 degrees before top dead center, we should be maximum cylinder pressure at 10 degrees after top dead center. That would be pretty good. But that's a 0.003 seconds for that pressure to build. So at higher RPMs, if it's a higher RPM, 0.003 seconds means we got to start it before 28. We might have to start at 38 or 35 or whatever, but they've calculated all that stuff and built it into your timing tables. And as technicians, we don't change those. Do you know why? You're modifying the emissions. One of us changes them. I've seen the car. I've seen the little laptop that you keep in your car.
Actually, I haven't touched my emission table. Yeah.
That's good. You've read some things. Ignition tables leave there's a lot of room right there to get more power, but there's also a lot of room right there to blow your engine up. So study up. This is high risk and high reward. All right, pretty good. And then when we start talking about the firing order, just remember, like, depends on the cylinder. They all have different firing orders. So it's nice when it's ECM controlled because the ECM controls when the coils fire and exactly what order and all those details. The computer does all that stuff. I highly, highly, highly prefer a distributorless ignition. Distributorless ignition is going to be all computer controlled, and I like that. But unfortunately, we do have to talk about distributors because that's where we come from, and they're still on some cars. And I think if you understand the distributor, you can understand this a little better too, right? So when we get on the inputs, remember we were talking about the timing tables? It's got to consider all these and possibly maybe more. The octane of the fuel, the engine load. So it can calculate engine load in several ways: intake air volume or manifold pressure, or sometimes manifold absolute um, mass airflow sensor. There we go. Stuck on manifold, right? So it's got to know engine load, but you can determine engine load a lot of different ways depending on the system. The RPM, the throttle position, right? So all of these are inputs to the computer, and then the computer has got this timing chart that it references and says, if this is this and that is that and that is that and that is that, then I should do this amount of before top dead center ignition timing. Okay. So like here it is a little bit more simplified. It's going to look at a bunch of stuff, like a whole bunch. Like if you have your throttle position sensor at wide open, that's going to change. That's going to add a level to the timing table that will indicate more advanced ignition timing. It'll look at all these things and then it'll say, okay, let's call for the coil to fire at 36 degrees before top dead center based on all these inputs. Okay, makes sense? So here's my thing to you. If we had a problem with, let's say, the engine coolant temperature sensor, we were looking at that a couple weeks ago. What do you think? What do you think the effect could be on your ignition timing? If your input is bad, do you think your output's going to be good? If you have these sensors that are messed up, do you think it's going to be able to get the most amount of timing advance on your engine? Exactly. So sometimes when you get a problem with some of these sensors, all of a sudden your engine won't have as much power. It might not have as good fuel economy and stuff like that. Yeah, that makes sense because your ignition timing is not going to be as advanced as possible. And see this one right here, the knock sensor? That one's going to be a really important one we're going to come back to. The knock sensor is a major input for ignition timing, okay? All right, but what about the types? How about old school, conventional breaker point? Cool. High energy electronic ignition, distributorless, which could be wave spark. And then COP or direct is also a type of distributorless, but we kind of separate those because this one, we diagnose it mostly the same, but it looks different. And so these could kind of be tag team, but we're going to separate them. All right, look at this. Conventional breaker point ignition. Look at this little piece of junk right here. When you spin a distributor, a little cam is going to bump this thing and it's going to close this points. And that's going to start the dwell, start charging the coil. And then you know what's going to happen? It's going to bump it open. And when it opens it, what's that going to start? Yeah, exactly. You want to see one of those in action? I was thinking the best way to show you this, I actually should have pulled it up ahead of time, but the best way to show you that is going to be, there's some animations, and I do have that as some of your homework, but I'm going to show you together so we can discuss it. Breaker point ignition. You're just going to be amazed. Like, it's so simple. It was a fun time when we did this. But it's going to be an animation, and I have an animation assigned for homework. Let me take a quick peek right here. That one I believe will do. I'm going to turn the volume off though. Okay, so I don't get popped for this. But you can always watch this independently, but if I talk you through it, I think it'll make a lot more sense. This one went into a lot of detail. No, there's one that's an animation. This one's not going to do it. Sorry about that. I remember it being a lot like this one. Let's have a look here. This one could be it. That one looks the most promising. I don't care about this sale. What are you trying to sell me? Yes, this is it. All right, so let's just show this right here. What's happening with this coil right now? Don't read their words. What's happening? It's charging up. This is the dwell time. Can you visualize it? It's charging. Yeah, it's charging it up. Cool. Uh-oh. Now when the engine cranks, this is going to be turned by the camshaft, okay? Now watch what it does. When it bumps that, do you see what it's doing? See how it opened it up? Well, let's talk about it. When it opens it up, what do you think is going to happen? It's going to switch over to the secondary, right? So right here, this is all primary. This is the switching device. Yep. When it does, and that's going to be shown right here is the primary. So we need to take a look at the secondary, which we're going to do in a moment. And this will be like a little condenser right here because it makes an arc. But when it opens that up, take a look at what happens. When it's closed, for example, you've got the coil, the primary coil is currents flowing through it, and that's creating this magnetic field. But exactly, when the breaker point's open, the current flow stops. But what happened, see, it's hard to even catch because it's so fast. But what happens is all that energy that was in the blue, making those magnetic fields, all gets induced into the secondary, which is red. Exactly. Yes. You see how simple the breaker points are? All it's doing is it's powering the primary and then not powering the primary. The second it changes over to not powering the primary collapses into the secondary, makes it that 12 or 20 or 40,000 volts, right? So that's the visual. And then once it makes that, once it collapses and there's an excessive amount of current in the secondary, that secondary's got to go somewhere, right? And that's kind of what we're saying here. 22,000 in this case. Boom, it's going to go over to the distributor. And the distributor, if you look, all the distributors have a center connection on the top in the middle. That center connection comes from the coil like this. That's where it's going. Like it looks like it's going in the middle, but it really goes over the top kind of. And then right here, you got 20,000 volts ready to go, but it's got no good path to ground, right? When it gets right here, notice it's not touching. But when it gets close to it, that gap's small enough, 22,000 volts can jump that gap. You want to see? Boom, do you see that? It jumped the gap. Now that one is on the distributor cap, and where'd it go? I don't know, we'll see. All right, so let's say that looked like spark plug 4. This looked like it was about maybe 3. I couldn't exactly tell, but right here, that spinning, this spinning thing is your distributor's rotor. It rotates and it points to these contact points on the cap. So this would be your distributor cap and your rotor. You see that little arc between the rotor and the cap contact points? That's gonna wear over time. That's why we needed to do a tune-up and replace the rotor and the cap. Okay. So this is a good system, but it needs a lot of maintenance, right? So here that rotor now goes to that one, and that one sends it to one spark plug. That one sends it to a different spark plug. That one sends it to a different spark plug. That one sends to a different spark plug. I just don't know which ones yet. I believe it pans out like right about here. All right, actually, I'm going to just back up right here. So let's just say this is cylinder number 4. When we're ready to spark cylinder number 4, we will do the spark I think I missed it. That bottom one was 4, right? So I don't know. Maybe that's 1. Maybe that's 3. Maybe that's boom. You see how it sent it to 4? Well, a little bit further ahead, you can see this is actually like we're missing one spark plug, but as soon as that distributor rotor points to the contact point on the cap, boom, it'll throw the secondary voltage down this big fat spark plug wire to that spark plug, and that secondary voltage will go through the spark plug. But when it goes to this center electrode, it's going to jump the gap right here, because this ground electrode, this strap right here, that's grounded because these threads thread into the cylinder head. So all this stuff is ground, and this one right in here is suspended in porcelain. So it's got the 22,000 volts till it jumps that gap. Kind of makes sense. So this is the secondary. Cool. And that's the old school distributor type. And you can pretty much see what's happening in the spark plug. There it goes. Gas ionization. Remember how it said that? When we have enough voltage, it'll align the electrons in the air fuel mixture and it'll make a current path, and that's the ionization. Sometimes I don't get too super into that, but it makes the spark. But the interesting thing is it can measure basically if the spark occurred by monitoring the conductivity between the secondary positive and the ground. So that way it knows if it actually occurred. It's an interesting thing. All right, so here you can see a visual. This is all primary stuff, right? If you look at it, the battery goes to the ignition switch powers the coil. The coil primary, what controls the ground on the coil primary? The breaker points. Yeah, so if you say somebody, oh, it needs new points, like my dad would tell me, I set the points with my matchbook. That literally meant he came down here, put his matchbook in there and tightened the screw, and that made the right gap. See, if your gap is too big, they might not touch, or they might, not stay together long enough, or, so this is the breaker points. That was under the cap. So this looks like it's separate, but really it's underneath this cap and rotor. You'd pull the cap off, you'd pull the rotor off, and beneath that would be the points, and you do your little things down there, replace a few things, and call it a tune-up, right? So that's a good overall. This is all the primary, but if you notice, this switching on and off, when it switches off, because there's no connection right there, because look, this goes to ground. So if we open this, there's no ground, which means it collapses the magnetic field, induces the voltage into the secondary coil, which is going to be high voltage, go to the center of the distributor. The rotor is going to point it to the distributor cap, which spark plug number 1, boom. Spark plug number 3, boom. Spark plug number 4, boom. Spark plug number 2, boom, right? So the distributor spinning just distributes the electricity to the right spot. The coil, however, is making the 22,000 volts. And the points are controlling the coil because the points are the switching device for the primary ignition. You like it? It's not that complicated, is it? You might have to think about it for a little while on your way home. All right, so we're pretty good on that. That's kind of what I was showing you right here, your breaker point system. That's literally the breaker point. You could replace these little points, and right in here, it would have a spinning part that's splined to the cam that would bump it open. All right, cool. That's pretty much the jam. Then we went away from that piece of crap. Ooh. So most of it was the same. It's just rather than breaker points, we'd have a pickup coil. And remember, the pickup coil would induce a little voltage right here when it got close, and that would send a signal to the ignition module. You know what the ignition module would do? Well, when it wasn't close, it would do the dwell. It would charge the coil up. But when it did get close, the ignition module electronically would open up B. You see B right here? So A is giving voltage to the coil, and B is giving ground to the coil. So it would go ahead and be like, you know what, B, open it. When it opens B electronically, what happens? starts the spark, right? So do you see how we went from this contactor going tick, 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 tick to instead this pickup coil is just measuring cylinder 1, cylinder 2, cylinder 3, cylinder 4, cylinder 5, cylinder 6. And when it gets close to, let's say 1, 2, 3, this is cylinder 4. When that little spinning part reaches cylinder number 4, sends the signal to the module, and the module says, B, take away the ground. When B takes away the ground, that's going to stop charging the coil primary, and it's going to induce the voltage to what? To the secondary. And it's going to send it to the same janky distributor that's going to wear out in 12 to 24,000 miles anyway. So we're still doing tune-ups because it's still got the cap and the rotor, but it wasn't quite as often because it no longer had the breaker points. It was making the ground and taking the ground through this ignition module. That was its job. Okay, see the progression there? So if you had an ignition module that wasn't pulsing ground, don't you think it could be the pickup coil? The pickup coil has to induce to show you where cylinder 1, cylinder 2, cylinder 3, cylinder 4, cylinder 5, cylinder 6 is, right? So you can no longer pop the cap off and see if the breaker points are touching. You have to actually electrically measure this pickup coil. See how it's not as cool anymore? And it's a little harder to do. And we bill more money for that. And the customers may not be happy about it, but the best thing I tell them is, well, go to the manufacturer and demand they go back to breaker points. And the manufacturers say, we can't meet our emission standards like that. And they're going to say, what? Who made the emission standards? And you know what they're going to say? The government. Vote them out. And people are going to be like, no, we're not going to do it. But at least they would know the truth, though. There's multiple layers of this thing. The reason that they're doing it was to meet emissions and fuel economy. And those are mostly good things, for the record. But if people are mad at the manufacturer because the cars become more expensive, they should probably figure out why the cars become more expensive. It's not just the Bluetooth stuff. There's more to it than that. So we've added this complicated thing. It's hard to diagnose, a little hard to fix. But you know what? I think it's kind of in our benefit because it gets more of the DIY people out of there. The more DIY people are retired because they can't work on it, the more work there is for the shop. Although sometimes there's too much, which is why my volume's down and I've already missed 2 phone calls. Want me to work on more crap? I don't really want to work on more crap. I can't walk today. Somebody else needs to know how to do this. Bail me out. All right, so the triggering device, a lot of times mounted inside the distributor. That was this thing. It's still inside the distributor because they couldn't figure out where else to put it yet. And that's why it's an ignition pickup coil. Cool. And then we're like, you know what? We're done with this distributor. This distributor is just too much maintenance. We go to a type of distributorless ignition. This one, you see these coils? What would you call that? Isn't that a coil pack right there? But look, they're in pairs of 2. So this is a waste spark coil pack distributorless. All right, so let's break this one down. This coil, for example, fires cylinder 5 and 2. So when 5 is on compression, TDC of compression, we want to fire it. And we're going to fire it on 2 as well. And 2 is going to be wasted, but 5 is going to be very productive. How do we know when to fire it, though? Well, look, we no longer have a pickup coil. Pickup coil's gone. The distributor's gone. You're looking for the distributor. You're not going to find it. Exactly. So this is distributorless. So look, we've got a camshaft position sensor and a crankshaft. Yeah, cam and crank right there. So these are going to give precise positions and speed information to a computer, which, like in this case, this is the ICM. This is the ignition control module. So this is a little early still, but the ignition control module is going to be like, all right, cylinder number 5 is at 10 degrees before top dead center. What should we do? Oh, I know. Turn off the ground to the primary coil, which will induce the voltage into the secondary coil, which will do what to spark plug number 5 and 2? Spark them. So ultimately, the ignition control module is controlling when the spark occurs, right? But to know when it should make the spark occur, it needs to look at camshaft and or crankshaft. Sometimes it looks at both. Sometimes it looks at one. Sometimes it looks at crank, and if crankshaft fails, it looks at cam. Sometimes it looks at cam, and if camshaft fails, it looks at crank to improve the reliability. And also, this can very, very fine tune adjust the ignition timing. So if we were to go back right here, when it was this, we had no way to advance or retard this. You just sparked it whenever it was set. Then they got into vacuum advance, which would physically pull the distributor over and advance it, but it wasn't real precise. Then we got into electronic advance, and this ignition control module could do some level of advancing, but this sucker right here can advance and retard the timing in a longer and a broader range, but can also do it very quickly. It's not going to be like, oh, give me a second. It's going to be like right now, right? There's no movement. There's no physical movement. It's all electronic controls. So this gives the ground and then takes the ground away exactly when it should based on its longer, more extensive timing tables. In old school like this, there was no timing tables. There was no ignition. There was no nothing. There was a little vacuum line that went over to this, or they had a mechanical advance. Remember those? They had a mechanical advance. The faster it spun, these weights would pull it and twist it a little bit, but like it was kind of not advanced. It was, if you wanted to tune it, you'd have to literally shave weight off the weights or add weight to it by trying to blob lead onto them or something. Like it was the greaser dog stuff, bust out the matchbook and, fine tune it a little bit. But we could adjust the base timing by rotating this with a wrench and a timing light. That's going to be in the service part. Then when we got to this, it was like this could do some of the advance and retard, but not much. Once you're into this, you're almost there. And the next logical sequence is we take this idea, we get rid of the waste spark plan, and we do either a coil on plug or a coil near plug. We've got 8 coils for 8 cylinders or 4 coils for 4 cylinders. And all of those coils are controlled by an ignition control module, but the ignition control module is generally going to be built into the ECM, and the ECM has access to all the sensor information. It knows intake air temperature, it knows coolant temperature, it knows your throttle position, your accelerator pedal position. It's looking at your knock sensor. It's looking at all these sensors to very, very, very precisely fine tune it. But go back in time. You used to just have breaker points open and closing. Does that sound expensive? To manufacture, to put on the first car, it's just one thing though. Think about it. If they want to make it, they're like, hey, let's make breaker points and something bumps them open. Zoom forward. You want it like this. You need a computerized module. Then you need this sensor, that sensor, this sensor, this sensor, that sensor, the other sensor, and you need 8 coils now. That's going to be way, way, way more money on the initial cost of the car. Would you agree? Car prices up. But the reason I don't think that's all bad is because this system need a lot of maintenance. This system, honestly, they don't need hardly anything. You just drive them and drive them and drive them and drive them. And if one of these coils goes bad, you replace one coil. And yeah, I mean, it gets kind of crappy when you're 150,000 miles and your first coil goes bad and there's probably 7 more that are going to follow. But from 0 to 100,000 miles, you know what you do with this system? Nothing at all. Nothing. So look at it from the manufacturer's perspective too. Their arm's a little twisted and they're like, hey, you got to meet these emission standards and these fuel economy standards. And they're like, cool, we'll do that. We'll research, we'll develop, we'll engineer, we'll design, we'll manufacture, we'll do all this stuff. And it's going to last, like if it only lasts 24,000 miles, they'd have to cover it under warranty, right? So it costs them. But if it lasts over whatever the warranty period is, 36, 50K, 60, whatever it is, 60,000, sometimes 100. As long as it's past the warranty period, do you know who has to pay for this? The customers, yeah. So it's kind of like, it is what it is. This is an amazing system for selling cars because it doesn't break. And they don't absorb the cost. They pass the cost off to the consumer, of course. And there's no real risk for them having to pay for the warranty. So like the manufacturers are cool, but what started it was being held to the emissions and fuel economy standards, just so you know. All right, so if you look at these, and the car's got 20,000 miles, there's probably no failure points. The car's got 150, 200,000. It could be the coils. It could potentially be a camshaft position or a crankshaft position sensor, right? You could maybe have some wiring. What if a mouse chewed this wire right here? What would the effect be? Can you tell what that wire does? Does that wire go to multiple coils or just to that one? If that wire's chewed, that coil's not going to work. And by the way, that is going to set a primary ignition circuit code because the ECM uses these small wires for the primary. You know where the secondary is on this system? It's just half of the coil and this little boot and this spark plug. The whole secondary ignition is just right here. That's it. In the coil and down in the tube. Down in the tube. Uh-huh. They do kind of. So these are usually made as an assembly, but sometimes this lower part right here can be a boot that you can service. But it's hard to say if that one was broken or normal. I don't think I've had one pop up. And it worked? Yeah. Normally it's all one piece, but they do have some boots that can be serviced. How about yours? Do your coils pop apart like that? I don't think so. Yeah. Well, you might not want to. All right, so if you look at this system though, let's talk about how we could diagnose this. What if you had no spark on any of the coils? Do you think it's this wire? I don't think so either. What would cause none of them to spark? Yeah, it could be the module. Could be the what? The battery? Well, then it isn't going to crank at all.
Exactly.
True?
Spark either.
True, but there would probably be a no crank, no start concern, don't you think? It goes click. All right, but if it goes shana no 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 no, it ain't the battery. But look, this module needs these sensors to work. So if you had a bad cam position sensor, don't you see how it could cause a crank no start? None of the coils will fire. Okay, make sense? Because remember, the module gives the ground and takes the ground away, but only based on the signal that it gets from the cam position or the crank position. Okay. In this way, it's not really all that different. It's just, it's not mechanical like this. It's electrical, which means inside the ECM, there's going to be a switch, but it's not going to be a mechanical switch. They're going to use a transistor, which is going to pulse the ground, give the ground and take the ground away. So the ECM uses a transistor to do it, which I do show you here. Right. And so when we look at old school coils, you know, we had a distributor that had one coil. And this coil, if you look at that frame, you might remember that frame from an earlier slide. That was a type of frame. This coil has to fire, if it's a V8, this coil has to fire 8 times for every 720 degrees of the engine. These coils get worked pretty hard. But if the coil fails, it's only one coil and you're done. Then if we went to the coil pack, this is going to fire for cylinder 6 and 3, this one for 5 and 2, this one for 4 and 1. So this has only really got to fire once per revolution, so 2 times for every 720. But this one also twice and this one also twice.
So older Jeeps have those kind of packs, right? Like
Everything used to have packs like this.
so my bike, Jeep Cherokee. We have a Jeep Cherokee, and it looks it's a circle with a bunch of wires.
No, that's a distributor. You have this. You have this. This distributor's turning. Remember that image we saw where the distributor's turning? You got that on that.
Okay.
But if let's say it was a 2005, you're probably going to have either this is the distributor style, that's the 95. You're probably going to have either this, or you might even get into the coil near plug or a coil on plug. Okay. This would be a coil on plug. This is modern.
They have six
Spark plug wires.
basically going into the engine.
Yeah, those are just the wires though. The coil's not there. Uh-huh. Yeah, that's an old school distributor. Yeah, that needs a lot of tune-up work.
Yeah.
Mm-hmm. So back in the day, if a customer came in, they were misfiring, it had a distributor, it'd be like, hey, we got to do a tune-up. When's the last time a tune-up was done? They're like, I don't know. Yeah, we got to do that. We just tune it up to start. But now, when you got this system, there is no tune-up. Okay, these coils don't have a maintenance interval. These coils don't need to be changed at 100,000 or 120 or 150. They get changed when they're no good. So we don't do this as a maintenance. We don't do sensors as a maintenance. The only thing we do on a maintenance on this one is the spark plugs. And you'll see if this has a like an iridium coated spark plug, that's like 120,000 miles. So if a car comes in that's running bad and it's an old car, we're probably like, hey, we should do a tune-up. Let's do your cap, rotor, wires, and plugs. And if that doesn't fix it, then we'll look into it. But we do the maintenance first. That's old school. New school is like, yeah, there is no maintenance. If you got a misfire, it needs diagnosis. And they're like, what? I don't want diagnosis. I just want a tune-up. And you're like, what are you going to tune up? You want to replace $900 worth of coils? Like, we need to find out what's wrong. We got to measure this. We got to check this. We got to check that. We got to check, you know what I'm saying? Like the days of the maintenance tech are less and less and less. They're not totally gone, but they're less and less and less. And so the people who pop the hood and they're just like, yep, those wires look old. Let's pop them off and put new wires on. That's not the future. The future is you do no maintenance and it comes in, you do minimal maintenance, I should say. Spark plugs at 120, and of course your oil changes and tire rotations, but with ignition, there's basically no maintenance. And it comes in, it's probably because something failed and it needs to be diagnosed. You don't just start jamming parts on there and shotgunning stuff and get that parts cannon out. Makes sense? Although that's what the mobile mechanic did, isn't it? Check the codes as a little bit of diagnosis, found it had a primary circuit code, slammed a coil on there, charged and left. What a mess. All right, cool. So again, when we look at the progression, right? A lot of maintenance, less maintenance, and this is probably even less maintenance, except we have a spark plug wire. So the better system gets to be like this. Right here, this is the coil. There is no spark plug wire. Spark plug wires need to be replaced. Coils directly don't, right? And so this one's a little bit of a pain in the butt, though. This might look familiar to you. Is a cassette style. The reason that these were not amazing is because the whole ignition coil and modules and everything were built into the top. So if you had a failure on one, you got to replace the whole assembly, which was kind of expensive. But when it came out, they're like, oh yeah, well, this won't really fail. They were so happy that this didn't need to be replaced all the time, like every few years. They're like, well, this should last at least 100,000 miles. And that was pretty cool at the time. But now you're like, no way, I want to get 250,000 out of it. And then you're shocked when you need a $700 ignition coil cassette assembly. And you're like, why'd they make this? Well, at the time, people were happy about it. But now that they're old, not so much. This one, the coil on plug, I got to tell you, I really do like this. When we get into coil diagnosis, you can see we can do that waveform and we can take a lot of measurements. We could do a lot of stuff. It takes time. It's a pain in my butt. You know why these are cool? If you think the number one coil's bad, unbolt it. Put it in cylinder 2. If the misfire follows to cylinder number 2, it was the coil. If it doesn't, it's not the coil. You got 6 coils or 4 coils or 8 coils or whatever. You can do some moving around to like do a substitute, a known good part type of thing. But if it doesn't follow it, then you still got to do more advanced diagnosis, right? But I do prefer these. I think it's a better setup. They're more expensive though. They could be 2-wire, 3-wire, 4-wire, 5-wire. So they're not all the same. But each coil requires 12-volt supply because that's what powers the coil. And then what do we need to do when we want to fire the coil? We give it ground and then we take it away. So we need a triggering signal, right? So in a little bit, when we start talking about the ignition control module still gives the triggering signal. We still need something to trigger the coil when to fire at the right time. Remember, that's the timing too, right? And so like this one, for example, is the ignition control module. And that's the control module for all those coils, for all those cylinders. And then when we get into that triggering thing, this is a Toyota specific slide, but I really like it because it helps people to understand. This is your coil right here. Actually, this whole thing is. And a lot of times your coil on the newer ones will actually have the triggering device inside of the coil, which means that's just got to get a signal from the ECM. So if the ECM sends the signal to trigger the coil, like Toyota would like to call it the IGT. So the ECM sends the signal. Basically, this transistor, you can see, is going to give, the igniter is going to give 12 volts to the coil right here. And this is the battery. It's going to give 12 volts to the coil on the primary. And then look, if this transistor is connected, it's giving it ground, right? So right now it's giving it ground. If this goes ahead and gives the correct signal, like let's say the signal in this case is 12 volts. If it gives 12 volts, it can open up this transistor. Or maybe this transistor is normally open, and while it's getting 12 volts, it makes it closed. Can you see how that would give ground? Trace it. Gives it ground. When it stops giving 12 volts, you know what it'll do? It'll open it, and that'll start the spark. Yeah, it'll collapse, go into the secondary, and fire the spark plug. Boom, the spark plug's here. Sorry, I went the wrong way. Right? But it's not really that complex. So if you had a coil that didn't work, you could make sure the coil has 12 volts. Then you got to go over to the triggering and see, is it getting a pulse? What's the pulse? It's going to be like ground, no ground, ground, no ground. And if you even had like a test light, you should see a flicker right there. Or if you had a meter, you should be able to, see a voltage jumping. But the best way to do it is probably to use a oscilloscope, and you can actually graph that and see what the transistors do. And the transistors opening and closing, that's its job. Make sense? And then if you were to see, like, a lot of times the ignition control module is really just the ECM, right? So the ECM is going to look at all the inputs, and then the ECM is going to control coil number 1 using IGT, ignition coil trigger, cylinder 1. So what else does the coil have? The coil has battery power, and then it has the switching, which is the ground. Cool. And that's really not that complicated. But in this case, though, there's one more complication. You guys can see the B plus, right? All those coils get positive. By the way, if this B plus had a blown fuse, what do you think would happen? All the coils would be down. Exactly. But if we had a cut wire on IGT1, that would affect just coil number 1. Exactly. So the diagnosis, I don't think, is all that complicated. What if we had no crankshaft position or no cam position? It wouldn't trigger any of them because it doesn't know the location, right? So you guys are getting this now. But there's one more thing. Do you see IGF? IGF is kind of weird. So this is what it is. IGT triggers it. IGF provides feedback. So a lot of times IGF is some sort of measurement of the ionization. Remember, if the spark occurs, it'll have some level of conductivity. It can measure the ionization. Sometimes IGF is really just a manufacturer's way of knowing if the spark occurred or not. So really the important parts of the coil are going to be the 12 volts and the trigger. And then the IGF could be a feedback. That's like the manufacturers wants to monitor the spark, because did you know if you don't get a spark, there's raw fuel in your cylinder? Do you know where that raw fuel gets pumped into? True, but first it goes through something in the exhaust. And the catalytic converter will get nuked like in a couple weeks or less. So the manufacturer's like, hey, if we don't have spark, we want to set a code quickly so that the customer brings it in right away so they don't fry the catalytic converter and have worse emissions, right? So a lot of times they'll do some level of feedback to say like, hey, there's not a spark, or this is one of the ways they monitor that the primary ignition is working or whether or not there's a spark. Typically, the misfire system usually uses the sensors. to see that the cylinder that was firing didn't speed up the crankshaft and camshaft. If it doesn't fire, the camshaft and crankshaft slow down. They don't speed up. So it's just trying to monitor itself, right? That's really where the F comes in. And then again, the crank and cam are inputs to the timing, but they also end up being the tattletales if there's a misfire, okay? And then again, you can see them, like this one's a crankshaft position sensor. So we got a sensor that's reading each of these teeth. Cool. And what we would do is graph that out, and we could look at camshaft pulses and crankshaft pulses. And then what's really crazy is if you look at these two and you look at a known good, you can actually tell. Let's just say that the CMP was really far forward and the CKP was really far backwards. That could actually tell you that your camshaft timing is off, like a timing belt or chain. So we can graph cam and crank and see a lot about the sensors, but also see a lot about the wheels. So if you had a broken tooth right here, a meter wouldn't show that, but an oscilloscope would, right? And also if we graph two of them at once, you can also tell if they're in line or if they're advanced or retarded. It's a little more advanced. Cool. And other types of sensors, so we have Hall effect sensors, and those can get just a little complicated, but essentially in a Hall effect sensor, when this tooth goes by that sensor, it'll create a Hall voltage, and the Hall voltage will give a signal to the ECM. So this digital output right here, that'll send a signal to the computer, and the computer will be like, oh, there's a pulse right there. A pulse right there means that there's a tooth right there. Now it knows its position. When that tooth is there, it should fire spark plug number 1, right? So if the Hall effect sensor sees the tooth and it gives that signal like this, there's a tooth, no tooth, tooth, no tooth, tooth, no tooth. That is going to be an input to the computer, and the computer is going to know when to fire the coil, right? It's going to know when to open that IGT, that trigger, and make the coil fire. Cool. But there are other types. Like a Hall effect is like this. Hall effect's very precise, much more expensive. It's more fast reacting. And then you have a cheaper magnetic cam sensor. This is a little harder to tell exactly where the part is, but we still will occasionally see a magnetic sensor. The magnetic sensor just creates an AC current when the tooth gets close. But the Hall effect sensor is like a powered, active, very precise, fast sensor that works all the way down to 0 RPM. This, when you're close to 0, the lines get so vague. It's kind of like, it's hard to really precisely control it at slow speeds. So we've gone more to these, but they cost more, right? You got to know which one it is to know which way to set the oscilloscope up. This is a DC signal. This is an AC signal. They're different sensors. They work different. If you need to test it, you need to put it on the right setting, right? So there you go. DC, AC. Totally different setup between these two. Cool. They both effectively do the same job, but we test them differently. And magnetoresistive is, it's like a little bit in between. So a few different types. It's a square wave, so that's DC. But it might not pull all the way down to 0. That's the main difference. The way we test them similar. All right, what about an optical? That's kind of interesting. We don't have anybody who's into the older GM stuff, like a 3rd gen Camaro, actually 4th gen Camaro, the Catfish Camaro. Yeah, like it could be a Z28. They had a distributor in there called the OptiSpark. Trash. They thought it was going to be so reliable, they put it behind the water pump, and when the water pump leaked, it went right in the distributor. But they were like, don't worry, we'll put it right back there. Nothing will ever fail. It had an optical pickup. So we can have those different sensors like this, right? But we could also use optical. So essentially what it's going to do is it's going to use an LED and a photodiode, and it's going to shine through these very, very precise little slots. And so if it's going around and you shine an LED and it shines through that hole, the photodiode will detect the light and it'll know that it's going through the hole. Then the light will go away and then it'll be back. And then go away and be back, go away and be back, go away and be back, go away and be back. You see what I'm saying? This is basically like fiber optics. Fiber optic Verizon Fios works like this. They're flashing the light really fast at one end of the glass fiber, and at the other end, it's picking up the pulses and it's communicating in like SOS Morse code style, right? So the optical was a cool idea because it's extremely precise, but they had some failures, so we've kind of gone away from this. This was also spinning part of the distributor. It's too big to put in a small sensor, so we're not generally using this anymore. Go ahead. 94 Camaro with a LT1. Trash. Yonke. 96, 97, but not, I forgot when it changed over, 99 or 98. But once they went to the LS, this was done. LT1 had this. A few other cars used some stuff like it. Yeah, and it looked good and it sounded good and they were pretty torquey, but this was a trash system. This system is garbage.
My mom had a 96.
Oh, it had it. Oh, it had. I bet you she had a distributor problem or
I
two.
mean, I think he was even missing like an odometer.
Oh yeah, no
Like a
judgment.
speedometer.
No
She was-
judgment.
She wasn't even.
They were
It
hoopties.
was junk.
But it was fun. It was fun. But so that's the thing. If you wanted to test this system, you got to test it way different because you're not able to probe onto it and measure voltage like this or like this. It was an optical test. So part of the reason I bring it in is it's just like there's so many different ways to trigger the ignition system. You got to have like a basic overall. You couldn't even see it. No, the thing is you could scope it, but you'd actually scope the photodiode, and it was like by the time it's behind the water pump, we're not really. A lot of times we're just like, you know what? You need a new OptiSpark distributor because it was so hard to really even test this system. It was horrible. Then we went more to like the coil on plug or the coil near plug. So this one I like, and you'll kind of see why. We talked about it just a bit. So it doesn't have a wire. It doesn't need a wire. It's got a single coil per cylinder. Beautiful thing. You can see this top will have the primary. You have the secondary. You have a conductor coming down and go into the actual spark plug. The wiring diagrams are going to be a little more simple because each coil is going to have its own trigger wire. They may call it trigger, they may call it signal, they may call it some different things, but this is where we're going to spend most of our time because this is what everything's gone to. There's advantages, eliminates the high tension cables, eliminates the spark plug leads, eliminates the cap, the rotor, all that, reduces interference. It's less resistance because it doesn't have long wires and multiple connections. It doesn't have as many concerns for like leaking voltage, which means arcing, right? So if you have a spark plug wire on the top of the valve cover and it arcs, what if you have a fuel leak where it's arcing? In fuego, right? You could have a fire right there. If the coil on plug only has secondary down in the tube, it's more safe, right? So this is just better in 1,000 ways. And a lot of times they can go 100,000 miles plus on average. And we are also doing longer life spark plugs, which we do cover, right? And because they only fire once per cylinder, we can increase the dwell time because they're not firing for every cylinder. They're only firing for their cylinder so they can reach their full potential. There's just a lot of benefits. And also because the higher energy arc, because the increased dwell time reaching its full potential, and also using different windings and less resistance, will allow us to run a more lean air fuel mixture. That's a big deal because if we can run more lean, that means we can have better fuel economy and potentially lower emissions as long as we deal with that oxides of nitrogen. Long as we deal with that NOx, which we do in a reduction catalyst, we can run lean and have low emissions, better fuel economy, but you couldn't do that with the old system, okay? So trust me, the old system is not going to come back. This one was improved in a lot of ways, except for initial cost to the customer. And this would be really common, pencil style coil. So yeah, sometimes you can replace a boot down here, but sometimes you can't. This silver is more of like a heat shield protecting the rubber insulator. Here is the cassette coil. This was not quite as good because you can't replace one. So it's kind of like coil on plug, but there's no separation. That's why it's a cassette. And they did have other types too, like a multi-strike was where they would actually spark the coil twice to make sure it had a complete burn. So if you were to ever scope one and you're like, what the heck? It's double sparking. If it has a multi-strike, that's normal. I actually don't even know what that's on, but
Would that be like if you have like if you're too lean, right? Too lean, too much gas in there?
no, it'd be more like incomplete combustion. So if you do a spark, but there's still a little bit of air and fuel left over, you're wasting energy and you're leaving emissions out the tailpipe. So they'll spark and then spark again, and that'll complete the burn. They've also got some like on a Nissan where it has two sets of spark plugs and two wires, and they're firing it both. They're firing both of them, or sometimes at the same time, or sometimes separate. They've done wild emissions, ignition stuff in the past in the pursuit of lowering the emissions. Okay, so just be aware. There's some funny stuff out there. And then we talked a little bit about waste spark. So waste spark is going to fire two coils, if you'll recall. One coil is going to fire two cylinders. So let's say this is cylinder 1 and 4. This one is on exhaust, so that's a wasted spark. This one's on compression, so that's a good spark. But then when the crankshaft rotates another 360, now this one's on compression, so that's a good spark. But this one's on exhaust, so that's a waste spark. So when you go to test a waste spark, just know it's going to have multiple firings, which means it's going to fire every revolution rather than every other. So you're going to have a different waveform. You go about it a little different. But if typically we had a problem on this primary or this secondary, it would affect both cylinders. If it's a coil, it's going to affect both cylinders because it uses one coil for both cylinders. If the spark plug's bad on one, but a good on 4, you might have a misfire on 1 and not on 4. That's not really like a coil. Okay, just some fun thing. And then this is kind of what it's showing. It gives 12 volts to the primary. The ignition module or the electronic module in general is going to give the ground to charge it up and then open it to fire it. And when it fires, it's going to fire kind of like this direction here. And then the next time the other direction. And so it's not really a big deal. But when you go to look at it, the compression spark on a waste spark is going to look like this. It's going to be a pretty high firing line because it's firing against compression. Whereas on the waste spark, when it's on the exhaust, it's going to be here, right? So sometimes you just got to know like which waveform is your actual one you're worried about. We're not really worried about the waste spark because that's on exhaust. We are worried about the power spark because that's on the combustion to the power stroke. It's kind of unique. And then we've got, when you just thought things were getting simple, we got another one called compression sense ignition, which uses even more circuitry in the modules. And it's going to monitor the amount of voltage it takes to ionize the space between each spark plug's electrodes. By monitoring it, they can tell when the air-fuel mixture has been ignited prior to spark jumping the gap. In the case of detonation or pinging, the PCM will likely retard the timing. All right, so what I'm saying is this compression sense ignition, it can measure the ionization as it's on compression. And if for some reason, all of a sudden it can tell there's a lot of ions lined up, it knows a spark occurred or a combustion has occurred before the actual spark occurred. So do you remember that term we had, like pre-ignition? Pre-ignition would be like the flame already started before the ignition fired. This system monitors that and doesn't need a cam position sensor. If it starts to see that there's ionization prior to the spark being commanded, it knows it's pre-igniting and it's going to retard the timing to back that off. So the way you diagnose this is even different, right? It's an interesting piece, and it also knows the greater the voltage level, the longer it's going to take to reach the point where it can jump a gap, and it can kind of do some self-diagnosis on the primary ignition side. Cool. But then the ionization should occur when enough electromotive force, which the voltage, is generated at the spark plug gap, and the atoms that make up the air-fuel ratio begin to ionize and conduct electricity. So it knows when the ionization is occurring. It's very different, right? And when the ionization stops, that tells it that the burn is over. So this system's similar, but has a different way of setting codes. It'll have some sort of ionization in the description. All right, so overall, it's similar, but a compression ignition system can set a cam position code without a misfire code because it doesn't really use that. For example, worn spark plugs or coils failing to fire can potentially set a cam position sensor code, right? So if you can't jump on and say, well, if it's got a cam position sensor code, throw a camshaft position sensor in it. This is saying worn spark plugs and coils can set that code. So there's a lot of stuff to know on that. But a good scan tool can check the current misfires. And if you got some misfires and it's got a cam position code, you might need to pursue the misfires before the cam position is even looked at, if it even has one. It's kind of interesting. All right, new term, spark knock. You ever heard of it? Bless you, because I just talked about if this sees, pre-ignition based on the ionization being early, it can tell that it's igniting too soon. Spark knock in general is when combustion will start in the cylinder, and then the actual spark will occur. And a lot of times you'll have two flame fronts colliding. It'll make a knocking sound. Sounds horrible. Go ahead. No, we're going to run this and then we're going to be done. Yep. Okay, so if this has spark knock, think of what that could mean. That could mean that the fuel and air is igniting prematurely, or that we have too high of a cylinder temperature or pressure. So why do you think that would be a concern? If we got the piston coming up, right? Remember our timing? Piston comes up, spark occurs. We want it to occur maybe 10 degrees before top dead center so it can get a good power stroke. What if the combustion occurs too early? Oh, it could start to push the piston down the wrong way. And so if we start to lose control of our combustion because of pre-ignition, detonation, or any of these types of sounds, the knock sensor will catch that and it'll say, whoa, we got an issue. We might need to retard the timing. We might need to rich in the fuel. We might need to take some corrective action. So when you start hearing the term spark knock, that's going to roll into knock sensor activity, which is all about making sure that the combustion is controlled. The combustion needs to start when the spark occurs, not too early. Makes sense? If it's starting too early, we're starting to lose control of it. We need to make some corrections. Okay, so we'll get a little bit more into the type of sensors. Oh, and another type. This is a combination coil unplug. So you see this? This is coil unplug, but why has it got two? Kind of similar to waste, but it's actually got two spark plugs in one cylinder. So it fires two spark plugs at the same time, but they're both in the same cylinder and they're both going to be fired on compression. So this would be like, this is actually a Hemi. So if you look, we got a big intake valve, a big exhaust valve. There's a big gap right there. To have a really clean burn, we might start a flame over here, which is going to go this way. But we could start a flame over here, which is going to go this way. And that'll decrease the amount of time it takes to get maximum pressure. So they'll end up actually doing either a combined coil, or this will be a 2-in-1 coil. It'll have two coils in one housing, and it'll fire both of these spark plugs. So the overall, it's going to promote combustion, by shortening how far the flame front must travel, right? So if it travels, this has only got to go halfway and this has only got to go halfway. That's important when you have a really big combustion chamber like a big Hemi, right? So the way that we diagnose these is even a little bit different because we might have to check 2 coils in one housing. It's kind of nuts. I know one group, when they were doing a compression test, they were on that Dodge and they were pulling spark plug after spark. They pulled 16 spark plugs out of a V8. And I was like, what is going on over there? Well, it had this. It had this system. Cool. And again, I don't want you to memorize every system. I just want you to know, I can't just tell you about ignition because there's like very, very many, lots of different variations and models. And then we talked about that spark knock thing. Well, here's an example of a couple knock sensors. This one threads in to, it could be like under the intake or in the head or something. And this one actually bolts in. This bolt goes right through. I tend to like these. This is a little more modern. But basically, the amplitude and frequency, so how loud the knock is and how often the knock is going to help determine what type of knock, right? So this is basically a microphone. And engines make noise, they got little taps and ticks and sounds, but this is programmed where if it looks at the amplitude and the frequency, it can tell like what's a multiple flame front combustion issue, and it can start to adjust the timing as a result. Okay, so the knock sensor is yet another of the many, many inputs that the ECM has to reference to control the timing and to control the ignition. Okay. All right. Yeah. And so we need this knock sensor to tell. So let's just say, you guys know if you have a high performance car, it calls for 91 octane, right? 91 octane because it's supercharged or turbocharged. You pick which one. Both. All 3, high compression, supercharged, and turbocharged, because America. We could do that. All right. That calls for 91 octane. But you know what? One day you're out of it, you forget, you pump 87. What do you think is going to happen? You're going to lose a lot of power. All right. So let me explain octane, because we're going to go into fuels too. Octane is the resistance to burning. Right? So if your piston's coming up and you got high compression, supercharging, turbocharging, high cylinder pressure, it's going to tend to break those bonds in the fuel and start a flame, right? The reason we use 91 is because it's going to hold on a little longer till we can start the spark. But if you accidentally shoot 87, it's going to start the flame before the spark occurred. No, there's not enough. There's only 87 octane rather than 91. So hold that thought. Some systems can measure the ionization and that it occurred before the spark and therefore know, hey, this is out of control. But most of them will use a knock sensor. And if you have a flame front over here and then the spark occurs and you have a flame front colliding, that's going to be like pre-ignition and detonation. It'll hear that in this microphone and it'll be like, oh, retard the timing. Don't give me 30 degrees before top dead center. Only give me 10. You lost a bunch of power, but it saved the engine. Yeah, that's good. Go ahead, Refugio. Uh-huh. 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 Yeah, you lost power. Sure. Yeah.
So after the rotation, then it gave power.
Uh-huh.
So then they told us to put
91.
yeah, and then fix it.
So there you go. If we hear spark knock, you may not hear it, but the knock sensor may hear it. It'll retard your timing, cut your power, but that'll save your connecting rods. Because remember, if we have pre-ignition, it's starting to build a flame front when the rod's still coming up, and it could push it down and punch that rod bearing in the face over and over.
Power, and then it gave.
It might have started. So a lot of times, if it hears the knock, it'll retard the timing quickly, and then it'll slowly advance it a little bit. So it's keeping you safe in a lot of ways. So this knock sensor is part of the ignition because it's a major input to the ignition system.
We lost when we started losing the pickup.
Yeah,
We lost the pickup.
sure. That's exactly why. Older cars didn't have that technology. Newer cars do, so they're a little more dummy proof, but it's also, what it also does is it allows the manufacturer to try to run as much advanced timing as possible for the better fuel economy, better emissions. But if it does overdo it, it can back it off because it's got a microphone listening all the time. Right. And then we get into the spark plug wires. This is secondary. So here's your high tension lead. There's your glass fiber core. That's the conductor. Then we got ferrite or EPDM. And then we've got some sort of a wrap and then a glass. And then we got silicone, right? You know why there's so many layers and thickness of insulation? Remember that part? This is the secondary high voltage. We got to contain that high voltage in the secondary. And that's why there's so much going on there. And that's why they tend to be a little pricey. And then if you've got some that you think might be bad, I'll show you a few tricks next time to test these wires out. Cool. So that's, the high tension cables, it's not a real super big deal. It also sucks when this nice brand new spark plug cable lays on the exhaust, like the header. If you got a new header, melts it, get another wire, because that'll make a direct short to ground and you'll have a misfire on that cylinder, that's for sure. Or just go ahead and grab it while it's running. You'll find out if it's good or not. But it won't kill you because it doesn't have a lot of amps. You could do it. All right. And then the final part's just spark plugs. Spark plugs are part of what? Primary or secondary? I agree. Secondary. So these are high voltage parts. So there's a lot about the types of spark plugs and whatever. So if you go to get spark plugs, you need to know a little bit. They need to be specific for that application. So if we've got a long reach or conventional, there's different reasons for each. This one has an iridium tip, for example. So if it's iridium, that's a different type of metal. It's most likely just a coating. It's probably not pure iridium. It's probably just a coating, right? So we'll come back to that too. And the spark plug, a lot of times it's going to go, in between, in the head, and it's probably going to be some water jackets and cooling stuff around. So we got to be really careful with these. They have different types. They could have a tapered type of seal, or they could have like a flat washer type of seal. If you have one, you can't put the other one in. It's all on how they seal to the head. Okay. So you got to pay a lot of attention and use the right spark plugs. They have thread size. So small spark plugs are a different thread size than larger spark plugs. They won't thread in, but also they have the reach length. So that'd be like if we go back here, see how this one's kind of short? Imagine if you took out a short reach spark plug and you put in a long reach. That's going to go further in the cylinder, right? Maybe so far that the piston hits it and you blow a hole in your piston. Make sense? So when people say like, oh, it's just spark plugs, it's easy. Well, there's a lot of things that could go wrong with changing spark plugs, especially if they're the wrong parts. That's really scary, right? And then also they have heat range or operating temperature. So there's colder plugs and warmer plugs. I'll show you a little slide as to what the difference is. But the important part is that spark plug will have a number on it. And that number is giving you all the details. Does it have a resistor? Is it short reach, long reach? Is it iridium? Is it copper? Is it laser coated? Is it whatever? All those numbers mean something, including the thread size too. Okay. And then this is the most common type. If you look, we've got the high tension. This is where the electricity is going to flow from the secondary, going to go straight through here, but we need to insulate it. Who thinks they know what the insulation is made out of right there? Not rubber, good guess. It's white. Porcelain, yeah. Similar, yeah. So typically porcelain, which maybe a type of ceramic. I actually don't. I think they're kind of in the same family. That could be true. I haven't tried. Are you an Antifa member? Okay. All right. All right. But what about when we're working on this? You think it'd be fairly easy to crack that porcelain or ceramic? Well, you don't think you could, what if you don't use a spark plug socket and your metal socket hits that? Oh, you'll bust it. Yeah. Or if you drop it from a height, you'll break it, so these are not real durable. You got to be careful. So when you use a spark plug socket, part of the reason why the spark plug socket has rubber, which will kind of like hold the ceramic, hold the porcelain, and keep the socket from getting crooked and hitting it and snapping it. So when you're changing these, just be gentle, be careful.
How bad is it? How bad is it to get pieces?
Not good. I'm not exactly sure what I would do with that, to be honest with you. I try to vacuum them out, try to blow them out. I try to get those out. And if I couldn't, maybe I'll try to start it and see what happens. But it's none of it's a good idea.
All you hear is pieces going out.
I bet you they'll probably bounce out the exhaust valve eventually. You just hope that when the
Because you don't, it gets to the point, you don't touch the walls that much. But
they'll probably get
one side,
my policy on that's going to be let's not find out. Let's not find out. How about that? All right. And then as it goes through the insulation, you'll notice this red is going to be positive, right? And it wants to make it to ground. You see the ground right there? This is grounded because it goes up and it attaches to the threads. And remember, the threads go to the head. So that's a good ground path. That's going to go to chassis ground. So the whole name of the game is to get the positive to jump the gap right there. Now that gap is a specified amount, right? So if we were looking at this, oh, and sometimes they even have a resistor or some other types of little details. When I go to change spark plugs, I always recommend OEM, whatever the car came with new. I don't try to put in some upgraded. I don't try to change it to hotter, to colder, to whatever. Just whatever OEM was. If it's a Ford, it's getting Motorcraft. If it's a GM, it's getting AC Delco. If it's Japanese, it's getting either Bosch or Denso, or if it's German, it's probably Bosch. Some take NGK, another Japanese brand. Whatever OEM is what I run. There's a lot of details on here. If you're hoping to get more horsepower, you're not going to get it by changing spark plugs to a higher performance spark plug with a fancier box. That's not how you're going to do it. And then as we get into here, like we were saying, this is a tapered type of seal. There's no gasket. These are the different sizes. Notice this one has a double ground electrode. That's kind of interesting. You may have some of that. And then that's a fun one, huh? And they, I'm not exact. I think it's actually to strengthen the electrode itself, because if you run these spark plugs too long, what'll happen is this electrode gets worn thinner, 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 thinner. But if it gets worn thinner to the point where it's just hanging by a thread, the electrode will actually break off and fall in. This is a stronger electrode. They're having issues with those breaking off and falling in. So that one's better. But then if you get into like the Spitfire plugs with 4 grounding electrodes, they have a lot of funky stuff, but I would run what's OEM. They did have these installed in some OEM. So that's legit. And then we start talking about the heat range. This next picture will make sense. So typically we're running around 932 to 1,742. Okay, that's the spark plug's typical operating range. If the temperature gets too low, the spark plug won't self-clean, right? So like basically, if you think of the carbon and the fuel and stuff, it kind of coats it. Like, you guys ever use a fireplace with a glass front? If your wood is wet and your fire's kind of cool, it'll get sooty in there. But if you keep throwing hard wood in there, good, like wood that's dried up, that's like oak or something, it'll get really hot and it'll incinerate all that darkness off the glass. That's self-cleaning. These self-clean too. But if they run too cold, they'll stay dirty. If they run too hot, they'll actually prematurely wear, and they could cause overheating. You could even see spark plugs melt down. But if you keep them right in a good range, they'll self-clean, they'll burn away the deposits, but they won't necessarily prematurely fail. So that's the engineers figured all that out. That's again why I'm saying run the original. Okay. But when you look at the spark plugs, this is going to be a hotter plug. If you notice, this gap right here is fairly small. That's going to keep the heat in and keep it pretty clean. If you run a colder plug, see how there's a bigger gap right here? There's more airflow coming through. That's going to run a little colder. Now there are times where, you know, if you're going to run nitrous or you're going to run some high performance, you may go with a 1-step colder plug or something, but that's not per the manufacturer. That's more per like the tuner with the experience. So because we're mostly concerned about repair, we're going to run OEM spark plugs. But at least now you can visualize one of the numbers on the spark plug is the actual temperature. And if you're too cold, it won't self-clean and you'll wear them prematurely. But if you're running the spark plugs you're supposed to, and it's OEM, they should last as long as the maintenance interval and maybe more. All right. And then when we get into talking about this gap, let's discuss this distance right here is called for by the manufacturer. Has anyone ever gapped spark plugs? Oh yeah, I probably did. So you take the spark plug out and use a little tool like this, and this is a wire type, or they have other designs and whatever, and you're gonna actually measure that gap. If that gap is too big, that's more resistance. That's harder on your coil, first off, because the voltage, the kV, the voltage for the firing lines can be high. Your firing line will be very high. So if you did a scope reading and your firing line was very, very high, there's a good chance you're going to pull the spark plugs out and you're going to find a big gap. How do you think the gap got so big? Over time in miles, a little bit of metal actually wears away and this gap gets greater and greater and greater. And that's why we have a spark plug maintenance interval. Old cars, 24,000 miles, 30,000, 36,000. New cars, 100, 120,000. How do you think we got the interval to be 120,000 stinking miles? To what type? What type? Okay. Close. And well, the coils and stuff all have an effect because the less often it fires, the better. But the thing is, when we get into platinum, iridium, etc. So look, copper tipped, combine the lowest cost with the shortest lifespan. So that's a cheap spark plug, but it's a good metal for conducting electricity. That copper, yeah, copper would be like a lawnmower. That'd be like a champion, you know, right? That's a cheaper, more basic spark plug in an older car. It's fine if that's what the car ran originally. Champions were good, but more what I mean was like Champion was a plug from back in the day. Champions aren't coming on any new cars. Yeah, so that's more what I mean. It's if you got a car that's got a distributor, cap rotor, and plugs, I'd run all the original stuff on that. I wouldn't go iridium on that because you're going to need to change your coil and your wires and all that stuff and your cap and rotor before the spark plugs are due. You're going to leave the spark plugs in there. It doesn't make sense. But if it's a new car, right? Like if we jump back to here, remember that this is going to be the latest and the greatest when we're talking about coil on plug. Cool. If you're going to run some of this newer stuff, this coil should last over 100,000 miles. So should your spark plugs. You don't want to, whoops, I blew right through that sucker. You don't want to be having to change like some of your parts and not all your parts. So in a way, we're using these fancy spark plugs only when we have the system that's going to last that long, right? And so when we got into, we were like right about here, when we start talking about gapping, when it's copper, it's all copper, you could gap it. When it's, let's say, platinum, the whole spark plug, I promise you, is not platinum. That thing be worth $1 million. So all they really do is platinum or iridium, they're going to put a coating just on the surface. So imagine if you have a small coating on that surface and you go ahead and you bring in this tool and you start prying against it and you're scraping against it, what's going to happen? You wear the coating off and you no longer have a long-lasting spark plug. You just brought it back to original Champion style. Make sense? Not that there's anything wrong with it. It's just when you're putting them in at 120,000, you're expecting them to be good for another 120. Not if you scrape that coating off, they're not. Right? And so they start putting these coatings on there. But you can see like if it was copper, maybe 20 to 40,000 miles. When you get into some of the iridium and stuff, it might not be quite as good of a conductor, but it's going to last much, much, much longer. It's also going to allow a more narrow gap. And so that's going to reduce fouling. There's some number of improvements, but let's say it's a platinum or an iridium coated. Should we gap them? You could verify the gap, but you don't have any business shoving something in there that's going to scrape it. You could basically look at it, and if it looks like it's good, it's good. Do you know what happens if you take an iridium spark plug and let's say the parts employee is walking and drops the box? Do you know what you're supposed to do? Junk that box and get a whole new box. I mean, it's pretty crazy because if the tip gets bent and you have to straighten it, it's no longer properly coated, you're done. Right? So you might hear this term, they're pre-gapped from the factory. Well, all the spark plugs come pre-gapped. They might just get messed up in shipping. If these get messed up in shipping, they're no good. That's also why they'll come with a little cardboard right here, a little protector to make sure that even if it does get dropped, it hopefully doesn't bend it. And so essentially that's the jam with these. If you take them out and they don't look like super fouled, like we looked mostly during engines, right, at the different type of fouling of spark plugs. Like if they look pretty good, we're good to go. We don't need to change them very often. If you do change them, it's mostly due to the miles. If your coil goes bad and it doesn't fire this, it won't get hot because there'll be no combustion. It can be fouled up and dirty. Then you may change the spark plug, right? But if your coils are lasting over 100,000, you're probably not going to have a coil failure. You're probably not going to have to do the spark plugs until either they're due or until you have a coil failure, which is at high miles. And then you're probably like, hey, we need to do this coil, and your spark plugs are also due based on maintenance. And so it's just not a tune-up. They're not coming in being like, hey, I need my spark plugs done at 24,000. It's more like, hey, it's 120,000. The car's 11, 12, 13 years old, and it's still got the original spark plugs in it every day. Totally normal. All right, so that is your introduction to ignition systems. Pretty intense. Hopefully you guys got any questions, you can ask them.